Hello there, and welcome to Science for Sleep, where we take complicated science, slow it down a little, and give it enough room to make sense without demanding that anybody stay awake for the entire explanation. Tonight, we're looking at something that does not announce itself with a visible explosion across the night sky. You could be standing outside beneath a perfectly ordinary set of stars, perhaps wondering whether you remembered to lock the door, while somewhere far beyond anything your eyes could see, a massive star reaches the end of its life and something extraordinary happens. For a brief period, space becomes flooded with X-rays. Not everywhere, thankfully, just from one distant point in the universe. The signal may last seconds, tens of seconds, or considerably longer, then it fades. By the time astronomers turn other telescopes toward the source, the brightest part may already be over. These events are known as X-ray flashes, usually shortened to XRFs. The name is almost suspiciously straightforward. Something flashes in X-rays, astronomers call it an X-ray flash, and everybody can go home early. Unfortunately, the universe rarely makes things quite that convenient, because when astronomers began studying these flashes carefully, they discovered that XRFs seemed strangely familiar. They behaved in ways that resembled another group of violent cosmic events called gamma-ray bursts. They could appear suddenly, release enormous amounts of energy, fade away, and sometimes leave behind a slowly weakening afterglow. Yet when compared with ordinary gamma-ray bursts, much more of their detectable energy appeared at lower X-ray energies rather than in the harder gamma-ray part of the spectrum. Observations by missions such as BEPISAX and Hyeste-2 helped establish X-ray flashes as a population closely connected with X-ray-rich gamma-ray bursts and classical gamma-ray bursts. Studies of HET-E2 events found that the three groups seemed to form a continuum rather than three completely unrelated families, which immediately created a rather interesting problem. If an X-ray flash is related to a gamma-ray burst, why is it mostly flashing in X-rays? Is the explosion weaker? Are we looking at it from the wrong angle? Is the material surrounding the dying star changing the radiation before it escapes? Is the engine at the centre behaving differently? Or are astronomers giving several names to different versions of the same basic event? That is where tonight's story begins. Before we go any farther though, where are you listening from tonight? And what does the sky look like outside where you are? Perhaps it is clear enough to see a few stars. Perhaps the entire sky is hidden behind clouds. Maybe you're in a city where the brightest object outside is not a star at all, but somebody's kitchen window. Or perhaps it is daytime for you, in which case the stars are still there, of course. They are simply being very politely ignored by the sun. Whatever is above you right now, there is something slightly strange about looking into the sky and knowing that most of the universe is invisible to human eyes. Our eyes detect only a narrow range of electromagnetic radiation that we call visible light. It is an extremely useful range. It lets us recognize faces, read books, admire sunsets, and locate furniture before walking into it at night. But the universe is producing far more than visible light. There are radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. They are all forms of electromagnetic radiation. They differ mainly in wavelength, frequency, and energy, and different cosmic objects can become much more noticeable depending on which part of that spectrum we choose to observe. A calm-looking patch of sky in visible light can be doing something much less calm in X-rays. Hot gas surrounding a compact object can glow strongly at X-ray wavelengths. Matter falling toward a neutron star or black hole can produce powerful high-energy radiation. Supernova remnants can shine in X-rays. Active galaxies can produce them, and when certain massive stars collapse, the resulting explosion may send an extraordinary high-energy signal across the universe. X-rays from space do not generally reach telescopes sitting comfortably in someone's backyard because Earth's atmosphere absorbs them. This is very good news for life on Earth, and slightly inconvenient news for X-ray astronomers. To study the X-ray universe properly, scientists have to put their detectors high above most or all of the atmosphere. using satellites and other space-based observatories. So an X-ray flash is not normally something a person sees. It is something an instrument notices. Imagine a detector orbiting Earth, quietly monitoring the high-energy sky. Most of the time it collects radiation from known sources and background activity. Then a new signal appears. There was nothing obvious there a moment ago, and suddenly the detector is registering a burst of X-rays from a particular direction. The signal rises. It changes. Perhaps it arrives in several pulses rather than one smooth burst. Then it weakens. The telescope has no idea whether anybody on Earth was awake, whether someone had just made tea, or whether an astronomer was currently arguing with a printer. It simply records the photons. Those photons may have been travelling for millions or even billions of years before reaching the detector. And that gives us one of the more peculiar features of astronomy. When we talk about detecting the death of a distant star, we're not watching it happen now. We're watching information about something that happened long ago finally arrive. The star may have disappeared before humans existed. Depending on its distance, Earth may have looked completely different when the explosion actually took place. Yet the radiation continued crossing space at the speed of light until a few of its photons reached a spacecraft carrying instruments built by a species that happened to become interested in exploding stars. Astronomy involves quite a lot of delayed correspondence. X-ray flashes are especially interesting pieces of that correspondence because they sit in a region of high-energy astronomy where the categories are not as tidy as their names suggest. A classical gamma-ray burst sounds fairly clear. There is a burst, and much of the prompt radiation is detected at gamma-ray energies. An X-ray-rich gamma-ray burst already makes things slightly less comfortable, because now the explosion has a larger proportion of its energy appearing in X-rays. Move farther towards softer energies and we reach the events called X-ray flashes. HET-2 observations showed comparable numbers of XRFs, X-ray-rich bursts, and classical gamma-ray bursts in one studied sample, with their spectral properties forming a continuous distribution. That was an important clue that astronomers might not be looking at completely separate mechanisms. They could instead be seeing different expressions of related explosions. That does not mean every question was suddenly answered. Quite the opposite. Once you suspect several mysterious phenomena are related, you have acquired the larger mystery of explaining why they look different. It is a little like discovering that three people with completely different outfits are actually members of the same family. Useful information, certainly. But now you would quite reasonably like to know why one is wearing hiking boots, one is wearing a dinner jacket, and one has arrived dressed for scuba diving. With XRFs and gamma-ray bursts, the differences involve energy, luminosity, geometry, speed, and the violent physics of stellar collapse. Some explanations propose that an X-ray flash can occur when the central engine produces a relativistic outflow that is less energetic than the jets associated with brighter gamma-ray bursts. Other ideas involve viewing geometry. A highly energetic jet may be present, but we might see it from outside its brightest central region. There are also models involving wider jets, structured jets, shock breakout, and radiation altered by material surrounding the star. The uncomfortable answer is that nature may be using more than one route to produce an event we classify observationally as an X-ray flash. Astronomers are used to this. The universe was not designed with our filing system in mind. Still, one particular event made the connection between X-ray flashes and dying massive stars much harder to ignore. On February 18, 2006, NASA's SWIFT satellite detected a remarkable event known as GRB 060218. Despite the GRB label, the event was unusually soft and is widely discussed as XRF 060218. It lasted much longer than a typical brief high-energy burst, and astronomers soon connected it with a supernova called SN2 006AJ. That association gave scientists something extremely valuable. They had a high-energy flash and a stellar explosion in the same event. Observations showed that XRF 060218 involved relativistic or mildly relativistic material, and an active central engine, while being much less energetic than typical cosmological gamma-ray bursts. It provided strong evidence that at least some X-ray flashes are connected directly with the deaths of massive stars and with the same broad family of engine-driven explosions that produces long gamma-ray bursts. We will return to that event later because it deserves more attention than a passing mention. For now, it gives us a useful picture to keep in mind. Somewhere inside a massive star, the final stages of stellar evolution have reached a point where the star can no longer continue as it did before. For millions of years, a massive star can survive because gravity pulling inward is opposed by pressure associated with the energy generated in its interior. The star is not sitting there peacefully because gravity has forgotten about it. Gravity is always trying. The reason the star remains a star is that its internal structure can resist collapse, while nuclear reactions continue changing the composition of its core and surrounding layers. As the star ages, that balance becomes increasingly difficult to maintain. Eventually, for a sufficiently massive star, the central region can no longer support itself in the same way. Then, events accelerate dramatically. A stellar lifetime measured in millions of years can end with physical changes occurring on timescales of seconds. The core collapses, matter moves inward at enormous speeds, densities rise, temperatures become extreme. The central region may form a neutron star or, under some conditions, continue collapsing toward a black hole. Around that compact central object, matter can continue falling inward. Magnetic fields can become intense. Rotation matters. Material can be heated and accelerated. In some explosions, an engine near the centre appears capable of launching narrow streams of matter outward at relativistic speeds. And when astronomers say relativistic, they do not mean the material is simply moving rather quickly. They mean its speed is high enough that Einstein needs to be involved. This is the territory of gamma-ray bursts. For decades, gamma-ray bursts have been among the most energetic transient events known in the universe. Long-duration gamma-ray bursts in particular have strong observational connections with the collapse of massive stars and certain Type 1c supernovae. Yet X-ray flashes present a softer version of the picture. Something powerful has happened. Something has accelerated matter and produced intense high-energy radiation. But the signal reaching us does not have the same spectral character as the classical gamma-ray bursts used as the original template. Imagine hearing thunder without having noticed the lightning. You know a storm is involved. The evidence is fairly persuasive. But you have not seen the event in the form you expected. An XRF creates a similar kind of scientific irritation. It resembles something astronomers understand reasonably well, except in exactly the way that makes them wonder whether they understand it at all. And this is one reason X-ray flashes are worth spending time with. They are not simply weaker gamma-ray bursts with a different label. Studying them tests what astronomers think they know about stellar death, relativistic jets, supernova explosions, compact objects, and how the orientation of an explosion affects what a distant observer detects. They also force us to think carefully about the instruments doing the detecting. Suppose two telescopes are observing the same event, but one is designed primarily for very energetic gamma rays, while another is more sensitive at lower X-ray energies. The event does not change because the telescopes are different. Our description of it might. A burst whose energy distribution peaks below the useful range of one instrument may appear unimpressive or may not trigger that detector at all. Another instrument with better sensitivity to softer X-rays might record a dramatic transient. This means that classifications in high-energy astronomy can depend partly on the physical object and partly on the window through which we observe it. That is not a flaw. It is simply something scientists have to account for. We do the same thing in ordinary life. Turn off the lights in a room and use an infrared camera, and suddenly objects that looked identical before may look very different, because temperature becomes visible. The room has not changed, your information has. High-energy astronomy works with the same basic problem on a much larger scale. The sky looks different depending on what kind of radiation you measure, And a dying star can send several kinds of information outward at once. There may be gamma rays, there may be X-rays. Visible light from a supernova can brighten later. Radio emission can develop as fast-moving material interacts with the environment around the star. An afterglow may persist long after the original high-energy flash has disappeared. Each wavelength gives astronomers another piece of the event. The first flash is only the beginning of the investigation. Once a satellite detects a transient, speed matters. Astronomers want a position. Other telescopes need to know where to look. X-ray instruments can continue observing the source. Optical telescopes can search for a fading counterpart. Radio observatories can monitor material expanding outward. Spectra can reveal properties of the explosion and its host galaxy. If a supernova becomes visible, its evolution can be followed over days and weeks. A few seconds or minutes of high-energy radiation can therefore turn into months of scientific work, possibly years. Scientists are remarkably good at turning a short flash into a long meeting. And somewhere underneath all those observations sits the central question we're going to keep returning to. What actually happened inside the star? Did its core collapse directly toward a black hole, while surrounding material formed an accretion disk? Did the collapse produce a rapidly spinning neutron star with an enormous magnetic field? Was a jet launched? How narrow was it? How fast did it move? Did it break cleanly through the star's outer layers? Did we view it from the side rather than looking down the jet? Did the radiation begin as something harder and become softened before it escaped? And why, when another massive star dies, do we sometimes see an ordinary supernova without any detectable X-ray flash or gamma ray burst at all? Those are not small questions. They touch the basic problem of how massive stars end their lives. Most stars do not produce gamma ray bursts. Most core collapse supernovae are not accompanied by the kind of relativistic outflow associated with GRBs and XRFs. Something special has to happen. Rotation is likely important. Magnetic fields may be important. The mass and structure of the star matter. Its environment matters. The geometry of the explosion matters, and the compact object left at the centre may matter enormously. But before getting buried inside collapsing cores, relativistic jets, shock waves, and neutron stars with magnetic fields strong enough to make ordinary magnets look embarrassed, it helps to understand how astronomers realized these strange flashes existed in the first place, because X-ray flashes did not arrive with helpful labels attached. No burst appeared in a detector carrying a note that said, "Hello, I am the softer relative of a gamma-ray burst. Please adjust your theoretical models accordingly." Scientists had to notice a pattern. They had to separate real cosmic events from instrumental noise and other X-ray transients. They had to compare the flashes with gamma-ray bursts. They had to measure how long they lasted, how their spectra behaved, where they appeared in the sky, and what happened after the initial emission faded. Only gradually did the picture become clearer, and even then the word clearer should be treated generously. High-energy astronomy has a habit of answering one question by introducing three more. Perhaps that is part of its charm. A telescope detects a signal. The signal suggests an explosion. The explosion suggests a collapsing star. The collapsing star suggests a jet. The jet suggests a central engine. Then somebody asks why the jet looked different from all the other jets, and everyone goes back to work. So settle in wherever you happen to be tonight. There is no need to remember every telescope name or every technical term. We will meet the important ideas more than once, and each time they will make a little more sense. For now, keep one simple image in mind. A satellite is moving quietly above Earth. Its detector is watching a part of the universe our eyes cannot see. For a while, nothing especially unusual happens. Then an X-ray signal appears from deep space. It is bright. It is temporary. It resembles a gamma-ray burst, but something about it is different. Somewhere at the source, a massive star may have just reached the last few moments of a life that lasted millions of years. The detector cannot see the star's core. It cannot watch the collapse directly. All it receives are photons, a brief delivery of information from an explosion that took place unimaginably far away. The first thing to know is that there was no single evening when an astronomer looked at a screen, saw an unfamiliar signal, and announced that a new kind of cosmic explosion had been discovered. Reality was less tidy than that. X-ray flashes emerged gradually from observations made by satellites that were already watching the high-energy sky for other reasons. The signals were there, recorded alongside gamma-ray bursts and all the other transient activity that makes X-ray astronomy such an interesting profession for anyone who enjoys being interrupted by the universe. One of the most important spacecraft in this story was Beppo Sachs, an Italian-Dutch satellite launched in April 1996. It carried several instruments designed to study X-rays and gamma rays, including 2 wide-field cameras that could watch large areas of the sky in X-rays and a separate gamma-ray burst monitor sensitive to much higher energies. That combination turned out to be especially useful because the satellite could effectively ask the same event 2 questions at once. Are you bright in X-rays? And are you bright in gamma rays? For ordinary gamma-ray bursts, the answer could be yes to both. Then astronomers began noticing events with a much stranger reply. Yes, and not really. The wide-field cameras detected sudden, bright X-ray sources lasting roughly tens of seconds to minutes. They appeared unexpectedly, behaved like transient events, and then disappeared. Yet some of them did not produce corresponding detections in Beppo Sachs's gamma-ray burst monitor. That was odd. The X-ray sky is full of things that can suddenly brighten, so a flash by itself is not enough to declare that something completely new has happened. Stars in binary systems can produce X-ray bursts. Neutron stars can flare. Accreting objects can change brightness. Solar activity can cause trouble. Instruments have backgrounds, noise, and all the usual complications involved in putting scientific equipment into orbit and asking it to measure individual photons. Astronomers therefore had to work out what these particular events were not before they could say much about what they were. The wide-field cameras helped because they could determine where a flash came from on the sky. If the same position repeatedly produced bursts, that might indicate a persistent or recurring X-ray source. If an event came from a direction associated with a known object, that was another useful clue. But some flashes appeared from apparently unrelated positions and looked remarkably similar to the X-ray emission already seen from gamma-ray bursts. Except for one rather important detail. The gamma rays seemed to be missing, or, more carefully, the gamma rays were weak enough that the gamma ray detector did not trigger on them. That distinction matters. Astronomers were not necessarily looking at explosions that emitted absolutely no gamma radiation. They were looking at events whose detected energy was heavily weighted toward the X-ray part of the spectrum compared with classical gamma-ray bursts. The difference sounds technical, but it changes the question considerably. If there were no gamma rays at all, perhaps these flashes represented an entirely separate phenomenon. If there were gamma rays, but far fewer energetic ones than expected, perhaps the flashes were related to gamma-ray bursts after all, and that possibility became increasingly difficult to ignore. Beppo Sachs had already transformed gamma-ray burst astronomy in another way. Before the late 1990s, astronomers had spent decades detecting gamma-ray bursts without knowing exactly how far away they were. Gamma-ray detectors could tell researchers that something had exploded, but accurately locating a short-lived burst on the sky was difficult. Beppo Sachs changed that because its X-ray instruments could provide much better positions for some bursts. On February 28, 1997, the satellite detected GRB 970228. Follow-up observations revealed fading X-ray emission, and optical observations found a fading counterpart. Soon afterward, another burst, GRB 970508, provided the first secure redshift measurement for a gamma-ray burst afterglow, confirming that at least some of these explosions occurred at cosmological distances. Suddenly, gamma-ray bursts were not mysterious flashes somewhere nearby in our galaxy. Many were enormous explosions taking place in distant galaxies. That made the strange X-ray events even more interesting. If they were related to gamma-ray bursts, They might also be signs of extraordinary explosions occurring across cosmological distances. What looked like a modest signal to a detector near Earth could represent a tremendous release of energy very far away. The difficulty was that the events did not fit the usual trigger system. A gamma-ray burst mission naturally expects gamma rays. That sounds almost too obvious to say, but it has important consequences. Imagine designing a burglar alarm that listens for breaking glass. It works very well when someone breaks a window. Then one night somebody quietly opens an unlocked door. Nothing is wrong with the alarm. It simply was not designed to react strongly to that kind of entrance. In a similar way, a burst dominated by softer X-rays might be obvious to an X-ray instrument, while looking much less impressive to a detector waiting for a strong rise in higher energy gamma radiation. So some of these events were effectively hiding in plain sight. They were not hidden because they were faint at every wavelength. They were hidden because astronomers had become accustomed to recognizing this general family of cosmic explosions through their harder gamma-ray emission. Once researchers started looking carefully through the Bipo-Sachs observations, a pattern appeared. John Heisey, Jean Intizand, Mark Kippen, Peter Woods, and colleagues described these events publicly around 2001. In the wide-field cameras, they appeared as bright transient X-ray sources, often lasting on the order of minutes, while remaining undetected by the spacecraft's gamma-ray burst monitor. Their X-ray properties looked strikingly similar to the X-ray counterparts of known gamma-ray bursts. The researchers called them X-ray flashes, a simple name for an inconvenient observation. At first glance, it would be easy to picture an X-ray flash as a normal gamma-ray burst with the volume turned down. But that is not quite right. A normal gamma-ray burst made weaker would simply produce fewer photons across its spectrum. An X-ray flash was interesting because its spectrum was softer. In astronomy, calling a spectrum soft does not mean it is gentle. A soft, high-energy spectrum simply contains relatively more radiation at lower photon energies. A hard spectrum extends more strongly into higher energies. It is a little like comparing two lamps. One may produce much more blue light, while another produces more red light. The distinction is not merely that one lamp is dimmer. Their light is distributed differently across wavelength. For X-ray flashes, the energy distribution shifted downward, compared with classical gamma-ray bursts. The peak of the observed emission could lie in the X-ray range rather than at the higher energies normally associated with gamma-ray bursts. And now the mystery became much more interesting. Why? One tempting answer was distance. The expansion of the universe stretches light travelling across cosmological distances. This process, called redshift, increases the wavelength of radiation and reduces the photon energy we observe. So perhaps X-ray flashes were simply ordinary gamma-ray bursts taking place extremely far away. A powerful burst might begin with a spectral peak in gamma rays, but after its light travelled across an expanding universe, that peak could be shifted into the X-ray range by the time it reached Earth. It was a reasonable idea. It also had the advantage of not requiring a new kind of explosion. Scientists generally appreciate explanations that solve a new problem using physics they already have, particularly when the alternative involves inventing an entirely new population of exploding stars before lunch. But distance could not comfortably explain everything. As observations improved, some X-ray flashes were found at redshifts that were not extreme enough to shift an ordinary gamma-ray burst all the way into the X-ray regime. High redshift might account for some soft bursts, but it could not simply be the universal explanation for the entire population. Later comparisons of X-ray flashes and X-ray-rich bursts with classical GRBs found that the high redshift scenario could explain some events, but not the whole sample. Another idea involved viewing angle. By this point, astronomers increasingly understood that gamma-ray bursts were probably not throwing their energy equally in every direction. Long gamma-ray bursts are associated with narrow relativistic jets. Picture a collapsing star launching two concentrated streams of material outward along its rotation axis, one in each direction. The material inside those jets can move at speeds extremely close to the speed of light. Radiation from relativistic material does something useful and slightly unfair. It becomes strongly beamed in the direction the material is moving. That means an observer looking nearly straight down a jet can see something enormously bright, while another observer viewing the same event from farther to the side may see something much weaker and softer. The explosion itself has not necessarily changed. The observer has. This gave astronomers an attractive possibility. Perhaps some X-ray flashes were ordinary or nearly ordinary gamma-ray bursts seen off-axis. Instead of looking into the bright central beam of the jet, Earth might lie just outside it. The harder gamma-ray emission would be strongly reduced from our viewpoint, while softer emission could still be detectable. If that were true, the difference between a gamma-ray burst and an X-ray flash could sometimes be no more mysterious than where Earth happened to be standing, cosmically speaking, of course. There is no recommended location from which to stand near a gamma-ray burst. Other models suggested that the jets themselves might vary. Perhaps some explosions produced very narrow jets, while others produced wider ones. Perhaps the energy was not evenly distributed across a jet at all, with an extremely energetic core surrounded by progressively weaker material. Perhaps X-ray flashes represented explosions with intrinsically lower energy, smaller Lorentz factors, or different conditions around the central engine. There were plenty of possibilities. What astronomers needed was a larger sample measured with instruments capable of detecting both X-rays and gamma rays, well enough to place these objects on the same scale. That opportunity came with another spacecraft. HETE-2, the High-Energy Transient Explorer 2, was launched in October 2000. Its purpose was to detect gamma-ray bursts across multiple energy bands and rapidly determine their positions so that other observatories could begin follow-up observations. For the X-ray flash mystery, HET-2 had an especially valuable quality. It was sensitive to relatively soft high-energy emission. Instead of treating the X-ray and gamma-ray skies as completely separate places, its instruments could study bursts across a broad enough energy range to reveal how one type blended into another. And they did blend. Over its first several years, HET-2 observed classical gamma-ray bursts, X-ray-rich gamma-ray bursts, and X-ray flashes. If those were three entirely separate populations, astronomers might have expected to see distinct groups. Perhaps one cluster of hard bursts over here, a separate cluster of softer events over there, and some conveniently empty space between them to make the classification easy. Nature declined to provide the empty space. In a sample of 45 bursts studied from HETE-2's first 3 years, researchers found comparable numbers of X-ray flashes, X-ray-rich gamma-ray bursts, and classical gamma-ray bursts. Their durations and sky distributions were similar. Their spectral properties were related, with the main progression occurring in quantities such as spectral peak energy, peak flux, and fluence. Most importantly, when the different types were plotted according to their X-ray and gamma-ray properties, they formed a continuum. That word, continuum, changed the way the problem looked. Imagine lining up cups of tea from almost entirely milk to almost entirely tea. You could place labels on them. Milky tea, normal tea, tea made by someone who apparently has a personal disagreement with milk. But if every possible mixture appears between those extremes, you would probably suspect that you're looking at variations of the same basic drink rather than three unrelated liquids. Something similar was happening with high-energy bursts. At one end were classical gamma-ray bursts with relatively high spectral peak energies and strong gamma-ray emission. Move gradually towards softer events, and you encountered X-ray-rich gamma-ray bursts. Continue farther, and you reached X-ray flashes. There was no obvious wall separating one group from the next. The evidence increasingly suggested that XRFs, X-ray-rich GRBs, and ordinary GRBs belong to a connected phenomenon, rather than being unrelated classes that happen to resemble each other. Of course, saying they were related did not explain the relationship. Two siblings can share parents and still behave very differently at weddings. Astronomers now had to understand which physical property was changing along this continuum. Was it total energy, jet angle, observer angle, jet speed, stellar structure, the nature of the object formed at the centre, some combination of all of them? There was another complication. The initial burst is only one part of a gamma-ray burst event. After the prompt high-energy emission fades, the outflow can continue interacting with gas and dust surrounding the explosion. That interaction produces afterglow radiation that can appear in X-rays, visible light, infrared, and radio wavelengths. Afterglows are extremely valuable because the prompt burst is brief and difficult to study. It arrives without warning and is often over before ground-based telescopes even know where to point. The afterglow stays around. It gives astronomers time to catch up. With an optical afterglow, researchers may identify the host galaxy and measure its redshift. With an X-ray afterglow, they can study how rapidly the emission fades. Radio observations can reveal the expansion and energy of the outflow, and if the event comes from the collapse of a massive star at a favourable distance, astronomers may eventually see the light of the supernova itself emerging beneath the fading afterglow. This is where an apparently simple flash becomes an investigation. First, a satellite notices a sudden increase in high-energy photons. Computers estimate the direction. An alert is distributed. Other observatories respond. Some are already in daylight and cannot observe the position. Some have clouds. Some are pointed elsewhere. Some can turn immediately. Large telescopes may interrupt scheduled programs because a transient event has appeared, much to the delight of the researchers studying the burst, and perhaps slightly less delight of whoever had been waiting 6 months for those telescope hours. Then the measurements begin. Is there a fading X-ray source? Is anything visible in optical images? Does the source brighten or fade in infrared? What galaxy lies underneath it? How far away is that galaxy? What does the spectrum look like? Does the light curve contain breaks? Does a supernova appear later? A burst that lasted 1 minute can produce weeks of observation and years of papers. X-ray flashes became much easier to take seriously once researchers could perform this kind of follow-up and see that their behaviour often resembled the broader gamma-ray burst family. They had afterglows. They occurred at cosmological distances. They showed connections with star-forming environments, and in some especially important cases, they were associated with supernovae. The idea that these were simply odd X-ray sources in our own galaxy became increasingly difficult to maintain. We were looking at violent events occurring in distant galaxies, yet compared with the most powerful gamma-ray bursts, many XRFs appear to have much lower observed peak energies, and in some cases dramatically lower inferred energy outputs. This did something useful for astrophysics. It expanded the range of explosions that theories had to explain. A model that works only for the brightest classical gamma-ray bursts is not enough if those bursts are simply one end of a much broader population. Now the theory has to produce the powerful gamma-ray events. It has to produce the softer, X-ray rich events. It has to produce X-ray flashes. And preferably it should explain why observations move continuously between them without requiring astronomers to add a completely new engine every time the spectrum becomes slightly softer. This is how an unusual signal becomes scientifically important. Not because it is merely strange. The universe contains no shortage of strange things. It becomes important because it challenges a boundary we thought we understood. Gamma-ray bursts had been named according to the radiation that first revealed them. Gamma rays. Then researchers encountered events that behave like members of the same family, while directing much of their detectable prompt energy into X-rays instead. The label stayed useful, but the physical picture underneath it had become more complicated, and there was still another issue. What exactly do we mean when we say that an event is dominated by X-rays? Where does an X-ray end and a gamma-ray begin? There is no sharp wall in nature separating the two. Both are electromagnetic radiation. A photon does not carry a small passport identifying itself as an X-ray before entering a detector. The names describe ranges of photon energy, and, historically, often how that radiation was produced or detected. In high-energy transient astronomy, researchers therefore needed practical definitions. One commonly used approach compares the amount of energy received in an X-ray band with the amount received in a gamma-ray band. If the X-ray fluence is sufficiently large relative to the gamma-ray fluence, the event can be categorized as an X-ray rich burst or an X-ray flash. Another approach looks at the spectral peak energy, usually written as E-peak, which tells researchers where the burst releases the largest amount of energy per logarithmic interval in photon energy. Classical gamma-ray bursts generally have higher observed E-peak values. X-ray flashes sit much lower, but again the distribution does not politely divide itself into separate boxes. HETE2's results made that particularly clear. The names are convenient. The underlying explosions seem to occupy continuous range. That should make us cautious when imagining an XRF as one specific object with one specific mechanism. X-ray flash is first an observational description. We detect a transient high-energy event with an unusually soft spectrum. Then we ask what physical event produced that spectrum. Those are two different steps. The first is measurement. The second is interpretation. And keeping them separate is important, because several very different physical situations can sometimes produce observations that look annoyingly similar. A weaker jet aimed directly at us might appear soft. A stronger jet viewed from the side might also appear soft. A burst seen at high redshift might have its spectrum shifted toward lower energies. Material around the source might influence the radiation. A shock emerging from the surface of a star could produce strong X-ray emission under certain conditions. Nature has options. Astronomers have data. Most of astrophysics is the process of introducing the two and seeing whether they get along. By the early 2000s, the basic observational mystery had therefore become clear. These flashes were real. They were not simply errors in gamma-ray burst instruments. They appeared repeatedly. Their durations and behavior resembled GRBs. Their spectra were much softer. And rather than occupying a completely isolated category, they seemed to extend the gamma-ray burst population toward lower spectral energies. The night sky had not revealed a completely separate language. It had revealed an accent. The more closely astronomers listened, the more familiar the structure became, even though some of the details sounded different. When a satellite records a burst of high-energy radiation, astronomers do not simply count how many photons arrived and decide whether the event felt sufficiently dramatic. They measure how the energy is distributed across those photons. That distribution is what makes an X-ray flash an X-ray flash. X-rays and gamma rays are both electromagnetic radiation. They are fundamentally the same kind of thing as visible light, radio waves, microwaves, infrared, and ultraviolet radiation. What separates the categories is mainly photon energy and wavelength. Visible light occupies the tiny range our eyes happen to detect. X-rays carry much more energy per photon. Gamma rays generally occupy still higher energies, although the boundary between X-rays and gamma rays is not perfectly defined. For high-energy astronomy, photon energy is often measured in electron volts. 1 electron volt is a very small amount of energy. Because X-rays and gamma rays are considerably more energetic, astronomers usually work in thousands or millions of electron volts. 1,000 electron volts is 1 kilo electron volt, written kilo electron volts. 1,000,000 electron volts is 1 mega electron volt, or mega electron volts. You do not need to keep those units neatly organized in your head tonight. The useful idea is simply that a photon at 100 kilo electron volts carries considerably more energy than one at 10 kilo electron volts. When a gamma-ray burst occurs, the detector receives photons across a range of energies. Some may fall into the X-ray band, others arrive at gamma-ray energies. Astronomers can sort those photons by energy and build a spectrum. Imagine placing every photon into a different box depending on how energetic it is. After the burst is over, you look at the boxes and ask where most of the energy ended up. A classical gamma-ray burst tends to place a large amount of its prompt emission at relatively high energies. An X-ray flash shifts that distribution downward. The event may still produce higher energy photons, but compared with a typical gamma-ray burst, far more of the observed energy is concentrated in X-rays. This is why simply calling an XRF a faint gamma-ray burst misses something important. Suppose you have two speakers playing the same song. Turn the volume down on one of them, and the music becomes quieter, but the balance between bass and treble remains roughly the same. Now imagine changing the equalizer instead. The volume may still be substantial, but the sound becomes dominated by lower frequencies. That is closer to what astronomers mean when they say an X-ray flash is softer than a classical gamma-ray burst. Soft does not mean weak. It means the characteristic photon energies are lower. A very energetic explosion can produce a soft observed spectrum, just as a comparatively weak event can still produce some high-energy photons. This distinction becomes especially important when scientists talk about something called the spectral peak energy. You will often see it written as E-peak. E-peak is one of the most useful numbers astronomers can extract from the prompt emission of a burst. In simplified terms, it tells them the photon energy around which the burst is releasing the greatest amount of energy in its observed spectrum. For many classical long gamma-ray bursts, that peak occurs somewhere in the gamma-ray range, often at tens or hundreds of kilo-electron volts, and sometimes much higher. For X-ray flashes, E-peak can be dramatically lower. In some events, it falls below a few tens of kilo-electron volts. In unusually soft examples, the peak can sit at only a few kilo-electron volts. That is a major difference. It means the entire energy distribution of the burst has shifted toward the X-ray part of the spectrum. HETE-2 made this particularly clear. Its observations showed that XRFs had much lower observed peak energies, peak energy fluxes, and total energy fluencies than classical GRBs, while other properties, including their durations and sky distribution, looked broadly similar. The populations blended continuously into one another rather than falling into completely separate groups. There's another word worth slowing down for here: fluence. Flux tells astronomers how much energy is arriving per unit area per unit time. Fluence tells them how much energy arrived per unit area over the whole event. Think of rain. Flux is how heavily it is raining right now. Fluence is how much water ended up in the bucket after the storm passed. For an X-ray flash, astronomers can compare the fluence measured in an X-ray energy band with the fluence measured in a higher energy gamma-ray band. That comparison provides a practical way to classify the event. During the HETE-2 era, researchers commonly compared energy received between roughly 2 and 30 kilo-electron volts, with energy received between about 30 and 400 kilo-electron volts. Events strongly dominated by the lower energy band were categorized as X-ray flashes. Events occupying the middle ground became X-ray-rich gamma-ray bursts. Those with proportionally stronger higher energy emission were classical gamma-ray bursts. This classification was useful because it relied on what the detector actually measured rather than requiring astronomers to know the physical cause in advance. And that is important because the physical cause is exactly what they were trying to determine. You detect the event first, you describe what you measured, then you begin arguing about what produced it. Science works much better in that order. Otherwise, there is a risk of deciding what an object must be and then becoming overly creative when the data refuses to cooperate. The classification also revealed something fascinating. There was no obvious gap. You could move from hard gamma-ray bursts to softer gamma-ray bursts, then into X-ray rich bursts, then into X-ray flashes. The spectrum changed gradually. That made XRFs look less like a separate species of explosion and more like one end of a large family. The first Beppo-Sachs XRF observations had already suggested this. Those events appeared as bright sources in the satellite's 2 to 25 kilo-electron volts, wide-field cameras, often lasting on the order of minutes, while failing to trigger the higher energy gamma-ray burst monitor. Their X-ray properties closely resembled the X-ray counterparts of ordinary GRBs. HETE-2 then gave astronomers a much better view of the transition between the categories. Instead of finding one population here and another over there, it found a slope. That raises an obvious question. If the populations form a continuum, why use different names at all? Mostly because names are useful. An astronomer receiving an alert that says a burst is an XRF immediately knows something about its observed spectrum. They know it is unusually soft. They know much of the prompt energy appeared at X-ray energies. They know its E-peak is probably lower than that of a typical classical GRB. That information helps decide which models might be relevant and which follow-up observations could be especially valuable. The name does not necessarily tell you what engine produced the burst. It tells you what the burst looked like. Those are not the same thing. This is similar to describing someone as very tall. That observation may be useful, but it does not explain why they are tall. Genetics may be involved, nutrition may matter, age obviously matters. Standing on a box would also change the observation rather dramatically. In astronomy, we have the additional inconvenience that many of our objects are billions of light years away and refuse to step off the box when asked. An X-ray flash therefore begins as an observational category. A short-lived cosmic source suddenly produces a burst whose energy distribution is unusually concentrated at X-ray energies. From there, astronomers have to ask why. One clue comes from duration. Despite the different spectra, XRFs do not generally form a completely separate duration population from long gamma-ray bursts. Many last tens of seconds, some last minutes. A few unusual events continue far longer. GRB 060218, one of the most famous X-ray flashes ever observed, had a duration of roughly 2,100 seconds in Swift's Burst Alert telescope. That is about 35 minutes. For a gamma-ray burst, 35 minutes is practically settling in for the evening. The event was also extremely soft. Its prompt spectral peak was around only a few kilo-electron volts, placing it firmly in X-ray flash territory. It occurred at a redshift of about 0.033 and was associated with the supernova SN2006AJ. That event matters because it demonstrates why definitions based only on duration can be misleading. You might imagine that an exceptionally long, soft event must have nothing to do with ordinary gamma-ray bursts. Yet XRF 060218 showed several connections with GRB physics, including evidence for relativistic or mildly relativistic ejector and a central engine. Its spectrum was different, its energy was lower, its evolution was unusual. But it was not simply an unrelated X-ray flare that happened to arrive at an inconvenient time. The high-energy emission, the supernova, and the fast-moving ejector were telling parts of the same story. This brings us to another important distinction: the prompt emission. When astronomers discuss an X-ray flash or gamma-ray burst, they often separate the event into stages. The prompt emission is the initial burst of high-energy radiation that triggered the detection. That is the part lasting seconds, minutes, or occasionally longer. Afterward comes the afterglow. The afterglow may appear in X-rays, visible light, infrared, and radio wavelengths. It is generally associated with the fast outflow interacting with material surrounding the explosion. An XRF is classified mainly from the properties of that prompt high-energy emission. The name does not mean the source emits only X-rays throughout its entire evolution. In fact, afterglow observations across many wavelengths are essential for understanding what happened. An event could begin as a soft X-ray-dominated burst, then produce an optical afterglow, radio emission, and eventually a visible supernova. The universe is not required to choose one wavelength and remain loyal to it. That would certainly simplify telescope proposals, but it does not happen. The prompt spectrum itself is usually not a simple spike at one energy. Instead, gamma-ray burst spectra are often described with mathematical functions that capture how the number of photons changes with energy. One of the best known is the band function. It is named after astronomer David Band, not after a musical group, which is useful because otherwise discussions about burst spectra would become unnecessarily confusing. The band function uses two connected power laws to describe a spectrum that changes slope around a characteristic energy. At lower energies, the spectrum follows one slope. At higher energies, it becomes steeper. From this shape, astronomers can determine quantities such as E-peak. Not every burst is best described by exactly the same function, and some soft events require additional components, but the general purpose is simple. The detector gives you counts. You determine how the instrument responds to photons of different energies. Then you infer the underlying spectrum that most likely produced those counts. That middle step is important. A detector does not observe the true burst spectrum perfectly. Every instrument has limits. It may be sensitive from, say, a few kilo-electron-volts to several hundred kilo-electron-volts. Outside that range, it sees little or nothing. Even within the range, its sensitivity varies. So imagine a burst whose true spectral peak occurs at 5 kilo-electron-volts. A detector designed mainly for photons above 50 kilo-electron-volts might catch only the high-energy tail. The event could look extremely faint. Another instrument sensitive down to a few kilo-electron-volts could see that same burst much more clearly. Neither telescope is wrong. They are sampling different parts of the same spectrum. This is one reason the discovery and study of XRFs depended so strongly on missions with good X-ray sensitivity. HETE-2 covered roughly 0.5 to 400 kilo-electron-volts across its instrument suite, allowing the same transient to be examined from soft X-rays into gamma rays. That broad coverage made it possible to see the connection between XRFs, X-ray-rich bursts, and classical GRBs far more clearly. There is a subtle lesson hidden here. The universe we discover partly depends on the instruments we build. Before humans had radio telescopes, the radio sky was effectively unknown. Before X-ray satellites, most cosmic X-ray sources were inaccessible because Earth's atmosphere absorbs X-rays. Before sensitive burst detectors, short high-energy transients could pass unnoticed. This does not mean the objects began existing when the instruments appeared. It means our categories are shaped by what we can detect. An X-ray flash from billions of years ago did not know that future astronomers would call it soft. It produced radiation. The radiation travelled. Our detector measured part of it. Then humans added terminology. There is another reason E-peak is so useful. It lets astronomers compare events without relying entirely on where somebody decided to draw the line between X-rays and gamma rays. Instead of saying only, this burst had lots of X-rays, researchers can say, the observed spectrum peaked near this energy. That gives a continuous quantity. A burst with an E-peak of 150 kilo-electron-volts is harder than one peaking at 30 kilo-electron-volts. A burst peaking at 30 kilo-electron-volts is harder than one peaking at 5 kilo-electron-volts. As E-peak decreases, the classification tends to move from classical GRB toward X-ray-rich GRB, and then XRF. Yet E-peak is only the observed value. This is where distance returns to complicate matters. If the source is far away, cosmic expansion stretches its radiation. A photon emitted at one energy can be observed at a lower energy by the time it reaches Earth. The farther back into an expanding universe we look, the greater that redshift can become. So astronomers distinguish between observed E-peak and the peak energy in the source's own rest frame. If a burst occurs at redshift Z, the rest frame peak energy is higher than the value we observe by a factor related to 1 plus that redshift. That means two identical explosions at very different cosmological distances would not necessarily produce identical observed spectra. This was one reason high redshift became an early explanation for X-ray flashes. Perhaps their radiation began as ordinary gamma-ray burst emission and was simply shifted into X-rays during its long journey to Earth. For some events, this effect can certainly contribute, but observations show that it could not explain the whole XRF population. Some X-ray flashes were simply too nearby. XRFO 60218 is an extreme example. At redshift 0.033, it was cosmologically close compared with many classical GRBs. There was nowhere near enough redshift to transform an ordinary hard burst into such a soft event. The softness had to be connected more directly to the explosion, the outflow, our viewing angle. or some combination of those factors, that leaves us with a useful working definition. An X-ray flash is a brief, transient high-energy event whose prompt emission resembles the broader gamma-ray burst population, but has an unusually soft spectrum, with a large fraction of the detected energy appearing at X-ray energies and a comparatively low spectral peak energy. That definition tells us what we see. It deliberately does not tell us why we see it. Because the why is still the interesting part. Several physical situations could potentially move a burst toward the XRF end of the spectrum. The explosion could be intrinsically less energetic. The jet could move with a lower Lorentz factor, meaning its material is not travelling quite as close to the speed of light as in a typical powerful GRB. The jet might contain an energetic central core surrounded by weaker material. We might be viewing the jet from outside its brightest direction. The jet could be unusually wide. Radiation could interact with material around the collapsing star. In some low luminosity events, shock breakout from the star or dense material surrounding it may contribute strongly to soft X-ray emission. Each possibility predicts somewhat different behaviour. That gives astronomers something to test. If viewing angle is responsible, perhaps the afterglow should evolve in a particular way as the jet slows and its radiation becomes visible over a wider angle. If the explosion is intrinsically weak, radio observations may reveal a correspondingly low energy in relativistic ejecta. If dense circumstellar material is involved, the spectrum and light curve may carry signatures of that interaction. If a central engine remains active for a long time, the X-rays may continue behaving in ways that a simple one-time explosion cannot easily explain. The label XRF therefore opens the investigation rather than finishing it. It tells astronomers that something has produced a burst whose energy distribution is softer than expected. Then every other measurement becomes evidence about the cause: duration, E-peak, fluence, redshift, afterglow brightness, radio emission, supernova properties, host galaxy, jet behaviour, thermal components. All of those clues help answer the question hiding behind the classification. What kind of stellar death can produce this? Long before an X-ray detector receives a sudden pulse from deep space, the event has already been developing inside a star for millions of years. Not every massive star ends its life with an X-ray flash, and most do not produce a gamma-ray burst either. That is important, because the basic collapse of a massive stellar core is actually fairly common on astronomical scales. The special part is what happens during and immediately after that collapse, when rotation, mass, magnetic fields, and the structure of the star can turn an already violent supernova into something even more extreme. To understand that, we need to begin before the explosion, while the star is still doing what stars spend most of their lives doing, trying not to collapse. A star contains an enormous amount of mass, and gravity is constantly pulling that material inward. The reason a living star does not simply fall into itself is that its interior is hot and pressurized, with energy generated by nuclear fusion helping to support the layers above. For much of a star's life, hydrogen nuclei in the core fuse into helium. That process releases energy. The energy moves outward through the star while gravity pulls inward. The result is a long-lasting balance. Not a completely motionless balance because stars are always changing, but stable enough that a massive star can remain luminous for millions of years. Eventually, the hydrogen in the central region becomes depleted, the core contracts, its temperature rises, helium fusion begins. Helium produces heavier elements, including carbon and oxygen. For a sufficiently massive star, the process continues. Carbon can participate in reactions that produce heavier nuclei. Later stages involve elements such as neon, oxygen, and silicon. The interior gradually develops layers with different compositions, often compared with an onion, although this is one onion you would strongly prefer not to cut open in your kitchen. At the centre, the reactions eventually produce large amounts of iron group nuclei. An iron creates a serious problem. Fusion has been useful to the star because combining lighter nuclei can release energy. Once the core reaches iron, that arrangement stops working in the same helpful way. Fusing iron into heavier elements does not provide the energy needed to support the star. Instead, it requires energy. The star has reached the end of the nuclear fuel sequence that has been helping hold gravity back. Massive stars race through their final burning stages much faster than their earlier ones. NASA notes that by the time silicon burning is producing iron, the available fuel can be exhausted on timescales of days, after earlier evolutionary stages lasted vastly longer. The iron core continues growing as material from surrounding layers is processed and added to it. For a while, another form of support helps. The core is so dense that the behavior of electrons becomes important. Quantum mechanics resists squeezing too many electrons into the same available states, producing what is called electron degeneracy pressure. It is a useful kind of resistance, but it has limits. As the core becomes more massive and dense, gravity gains the advantage. Then two processes make the situation deteriorate rapidly. High-energy photons begin breaking iron nuclei apart in a process called photodisintegration. Instead of releasing energy, this absorbs it. At the same time, electrons can be driven into protons, producing neutrons and neutrinos. That reduces the number of electrons available to provide pressure. So gravity is pulling inward, while two of the mechanisms that had been helping resist collapse are being weakened. The change is sudden. The core begins collapsing. And once that begins, there is no leisurely stellar discussion about whether this is really the best course of action. The inner region falls inward at enormous speed. Matter becomes compressed to densities that are difficult to picture in ordinary terms. Atoms do not remain intact in the familiar way. Electrons and protons are driven together. The core becomes increasingly neutron-rich. Within roughly a second, a central region thousands of kilometers across can collapse to something only tens of kilometers across. NASA descriptions of core collapse events emphasize just how abrupt this final contraction is compared with the millions of years that preceded it. For the collapsing matter, the journey inward eventually encounters resistance again. At nuclear densities, matter cannot simply compress indefinitely in the same way. The inner core stiffens. In many core collapse models, the innermost material halts its collapse abruptly and rebounds. Material that was still falling inward crashes into that suddenly stiffened central region. A shock wave forms. At first glance, that sounds like the explosion. The core collapsed. It bounced. The shock moves outward. Star explodes. Everyone can return to the telescope. Unfortunately, the real mechanism is more difficult. The shock loses energy as it moves through material still falling inward. Breaking apart heavy nuclei consumes energy. The shock can stall rather than immediately racing through the entire star. That stalled shock is one of the central problems in the physics of ordinary core collapse supernovae. Meanwhile, the newly formed compact object is releasing a staggering number of neutrinos. Neutrinos are subatomic particles that interact very weakly with matter. Most can pass through enormous amounts of material without hitting much of anything. Under normal circumstances, this makes neutrinos rather antisocial particles. During core collapse, however, the densities and temperatures are so extreme that neutrinos become central to the process. The forming neutron star releases tremendous energy through neutrinos. A small fraction of that energy deposited behind the stalled shock, together with turbulent motions and other effects in the collapsing star, can help revive the outward moving shock. The exact details are a major subject of supernova modelling, and the explosion does not behave like a perfectly spherical shell moving smoothly outward. The collapsing star is turbulent. Material flows in different directions. Instabilities grow. Rotation can distort the geometry. Magnetic fields can become important. The simple picture of a star collapsing neatly toward its centre and then exploding evenly in every direction is useful for a first sketch, but real stars are under no obligation to remain simple for our convenience. What survives in the centre depends on the conditions of the collapse. One possible result is a neutron star, A neutron star contains roughly stellar amounts of mass compressed into an object only around the size of a city. Its density is extraordinary. A person standing on its surface would have more immediate concerns than density calculations, largely involving the fact that standing there would not be possible. If the collapsing core and later infalling material produce a remnant that cannot remain supported as a neutron star, the collapse can continue until a black hole forms. For the explosions connected with long gamma-ray bursts and at least some X-ray flashes, that central outcome becomes especially interesting. An ordinary core collapse supernova does not automatically produce a relativistic jet. Something more organized has to occur near the center. The star must somehow take part of the enormous gravitational energy released during collapse and direct it into a narrow outflow moving close to the speed of light. One widely studied route is the collapsar picture. In the basic version, a massive, rapidly rotating stellar core collapses and forms a black hole. But not all surrounding material falls directly into the black hole. Why not? Because it is rotating. Matter carrying enough angular momentum cannot simply drop straight inward. Instead, it can circle the black hole and form an accretion disk. You can see a less extreme version of the same basic idea when water rotates around a drain. The comparison stops being useful fairly quickly, since a kitchen sink normally contains neither relativistic plasma nor a newly formed black hole. Still, the essential point is rotation. Material in the disk spirals inward. As it moves closer to the black hole, gravitational energy is released. The disk becomes extremely hot. Magnetic fields can become amplified and reorganized. Under suitable conditions, part of the material and energy can be redirected away from the central region, along the rotation axis. Instead of everything falling inward, two narrow outflows can emerge in opposite directions. Jets. NASA's current descriptions of the standard long GRB picture connect these events with massive, rapidly rotating stars whose cores collapse, often producing a black hole and relativistic jets that penetrate the star. The existence of a jet does not mean the jet has escaped. That is an entirely separate problem. Remember where the central engine is located: inside the star. The newly formed black hole or neutron star is buried beneath enormous amounts of stellar material. A jet launched near the center has to push through that material before it can emerge into space. Picture trying to fire a very narrow stream upward from the center of an object, containing several solar masses of dense gas. The jet moves extremely quickly, but the material around it is not empty space. As the jet advances, its leading region drives a shock into the star. Material around the jet becomes hot. Pressure builds. Some of the jet's energy spreads sideways into a hot region surrounding it, often described as a cocoon. The jet is therefore not simply flying through a convenient tunnel. It is creating the tunnel while the star is collapsing around it. Whether the jet succeeds depends on several things. How powerful is the central engine? How long does it remain active? How dense are the stellar layers above it? How large is the star? How narrow is the jet? How much energy does it lose while forcing its way outward? A powerful jet that remains active long enough may reach the surface. Once it breaks free, relativistic material can expand into space. Somewhere in that process, through mechanisms that researchers are still working to understand fully, enormous amounts of high-energy radiation can be produced. If the geometry and spectrum are favourable and the jet is directed toward Earth, we may detect a classical long gamma-ray burst. But imagine that the central engine stops too soon. The jet begins drilling outward. It makes progress. It heats the surrounding material. Then the supply of energy weakens before the jet reaches the stellar surface. The jet can stall inside the star. Astronomers sometimes refer to this as a choked jet. From far away, that event could look very different from a successful classical GRB, even though the central engine began with a similar idea. This possibility is important for the broader family of weak gamma-ray bursts and X-ray transients. NASA has described cases such as GRB2000826A in terms of a burst from a collapsing massive star whose jet may have been close to failing, showing that even duration categories can become misleading when the engine or jet behaves differently from the usual pattern. There is also another possible engine. The collapse may produce a neutron star instead of immediately producing a black hole. If that neutron star is rotating extremely rapidly and possesses a very strong magnetic field, it can store an enormous amount of rotational energy. Such an object is often called a magnetar when its magnetic field reaches exceptionally high strengths. A newborn, a rapidly spinning magnetized neutron star can transfer rotational energy into the material around it. In some models, that energy can power a relativistic outflow and contribute to an explosion that resembles the broader gamma-ray burst family. So when astronomers speak about the central engine of an XRF or long GRB, they are not always claiming that the answer is definitely a black hole. Depending on the event and the model, the engine might involve a newly formed black hole and accretion disk, a rapidly rotating magnetized neutron star, or a transition between different stages as collapse continues. The radiation arriving at Earth does not provide a photograph of the engine, it gives clues. That is why events associated with nearby supernovae are particularly valuable. They allow astronomers to compare the high-energy burst with the visible explosion, the expanding ejecta, the radioactive material produced in the supernova, and later radio or X-ray signatures. Each measurement reduces the number of ways the hidden central engine can behave without being noticed. Another piece of the story involves the outer structure of the star before collapse. Many long gamma-ray bursts are associated with Type 1c supernovae. Those are core collapse supernovae whose spectra show that the progenitor had already lost its outer hydrogen layer and also much or most of its helium. In other words, the star reaching collapse may be far more stripped down than the enormous red supergiant people often imagine when they hear the words massive star. One important class of stripped massive stars is the Wolf-Rayet stars. These objects can lose substantial amounts of their outer material through stellar winds or binary interaction before the core collapses. That stripping matters for a jet. A compact stripped star gives the jet less distance to travel before escaping. A large star with an extended hydrogen envelope gives it considerably more material to cross. NASA discussions of long GRBs have specifically noted that stripped Wolf-Rayet-like progenitors are attractive because a compact star allows a relativistic jet to drill through the stellar body on the timescales associated with ordinary long bursts. Rotation complicates this picture. A strong relativistic jet requires a central system capable of maintaining considerable angular momentum. Yet massive stars can lose angular momentum through stellar winds as they lose mass. A star therefore needs to reach its final collapse in the right condition. Massive enough, rapidly rotating enough, stripped enough for a jet to escape, possibly interacting with a binary companion, possibly evolving in an environment where weaker stellar winds allow it to retain more mass and rotation. There is no single switch labelled Make Gamma Ray Burst. The progenitor's entire history matters. Two stars might begin their lives with similar masses but reach collapse with very different rotation rates, because one interacted with a companion. Another may lose more of its envelope. Another may merge with a nearby star. One may form a neutron star. Another may form a black hole. One jet may escape. Another may stall. One observer may sit near the jet axis. Another may view the event from farther to the side. By the time the radiation reaches a distant detector, all of those differences have been compressed into a light curve and a spectrum. That is the difficult part of the investigation. Astronomers see the result. They have to reconstruct the machinery. Consider what happens to the timescale as well. The star lives for millions of years. The iron core develops near the very end. The final collapse happens in seconds. A central engine may operate for seconds or minutes. The jet crosses the star. The prompt high-energy burst reaches space. Then the supernova continues expanding for days, months, and years. The sequence contains processes with timescales differing by enormous factors, yet the X-ray flash may be determined by a very small portion of that history. A difference lasting only several seconds near the centre could determine whether the jet escapes cleanly. A slightly different amount of rotation could change how the accretion flow develops. A different viewing direction could change the photon energies we detect without altering the basic explosion. This is one reason scientists are careful when connecting every XRF to one exact physical scenario. The observational category is broader than a single engine model. Some X-ray flashes are closely associated with supernovae. Some look like softer extensions of ordinary GRBs. Some low luminosity bursts may involve additional effects such as shock breakout, and not every apparently soft burst must have become soft for the same reason. Shock breakout introduces another route for X-rays to appear. When a supernova shock travels outward through a star, it eventually approaches the surface. While the shock is deep inside, radiation is trapped by the dense material around it. Near the outer edge, the density becomes low enough that radiation can escape. That moment is called shock breakout. It can produce a brief burst of energetic radiation, often in ultraviolet or X-ray wavelengths depending on the properties of the star and its surrounding material. If the star is surrounded by a dense wind, the shock may effectively break out in that wind rather than exactly at the visible stellar surface. Now imagine observing an engine-driven stellar explosion in which several components may contribute at once. There is the central engine. There may be a jet. There is hot material around that jet. There is a supernova shock moving outward. There may be dense gas previously lost by the star. There are relativistic particles interacting with their surroundings. All of those components can produce radiation at different energies and times. What we call the X-ray flash may therefore be dominated by one component in one event, and another component in a different event. That sounds frustrating. It is also useful. Different mechanisms leave different signatures. A thermal signal may suggest radiation emerging from very hot material with something closer to a characteristic temperature. A non-thermal spectrum suggests particles and radiation processes that cannot be described by a simple hot surface. The duration tells us something about the engine or emitting region. The afterglow reveals how fast ejecta interact with their surroundings. The supernova tells us about the star itself. Radio observations can test whether substantial relativistic material was launched. The puzzle is difficult, but it is not without evidence. And perhaps the easiest way to appreciate how unusual an X-ray flash is would be to imagine all the massive stars that do not produce one. A core collapses somewhere. A neutron star forms. A supernova shock emerges. The outer layers are thrown into space. The star becomes brilliantly visible for a while. No relativistic jet points toward Earth. No brief X-ray dominated signal reaches one of our satellites. From our perspective, it is an ordinary core collapse supernova, still violent, still capable of creating and dispersing elements, still one of the most energetic events a normal star can produce. But no XRF. Another star collapses. This time, rapid rotation helps organize an engine around the center. A jet forms, it survives, it reaches the surface. The relativistic outflow produces a bright, hard, high-energy burst directed toward us. Our detector sees strong gamma radiation. We call it a long gamma-ray burst. Then somewhere between those outcomes lies the territory that has been giving astronomers trouble. A jet may be weaker. The engine may be less energetic. The jet may carry less relativistic energy. It may struggle while crossing the star. It may be viewed from outside its brightest core. Shock-related emission may contribute more strongly. The result reaches our detector with its spectral peak shifted downward. The explosion still bears the fingerprints of the same violent stellar death, but instead of announcing itself primarily in gamma rays, it arrives more softly in X-rays. A long gamma-ray burst can begin with the same basic situation we have already followed into the center of a massive star. The core collapses. A compact object forms. Material continues falling inward. A central engine releases energy. Under the right conditions, a jet is launched, and pushes through the surrounding star. If the jet escapes, and its fastest material moves toward us at nearly the speed of light, the result can be one of the brightest high-energy events visible across the universe. An X-ray flash can emerge from the same broad family of stellar deaths and still look surprisingly different. That is why calling it the quiet cousin of a gamma-ray burst is useful, as long as we remember that quiet is a relative term. The star has still collapsed. A supernova may still be developing, material may still be moving at relativistic speeds, the central engine may still be producing enormous amounts of energy. It is only quiet when compared with something so energetic that it can briefly outshine almost everything else in the gamma-ray sky. There are several ways for two related explosions to appear different, and one of the most important involves direction. Gamma-ray bursts are strongly affected by beaming. The energy does not necessarily leave the star equally in every direction. A substantial part can be concentrated into narrow jets. If one of those jets happens to point toward Earth, we receive a much stronger signal than an observer located far from the jet axis would receive. This matters because relativistic motion changes the radiation we observe. Suppose a source of light is moving toward you at an ordinary speed. You may see some change in its frequency and brightness, but nothing especially dramatic. Now increase that speed until the emitting material is moving at more than 99% of the speed of light. The situation changes considerably. Relativistic effects concentrate much of the radiation into the direction of motion. The observed photons can also be shifted toward higher energies, and the event can appear brighter and shorter. Astronomers describe part of this using relativistic Doppler boosting. The basic idea is familiar from sound. When an ambulance approaches, its siren sounds higher in pitch. After it passes, the pitch drops. Light has a Doppler effect too, although relativistic jets require Einstein's version of the calculation. When material races almost directly toward us, radiation from that material can be strongly boosted. This means a classical gamma-ray burst is not merely an enormous explosion. It can also be an enormous explosion viewed from a particularly favourable direction. Favourable for astronomy, at least. Being physically close to the jet would be less favourable. Now move the observer slightly away from the centre of that jet. Nothing about the star itself has to change. The black hole does not notice. The accretion disk does not pause and complain that Earth has moved. The jet continues outward. But the radiation reaching the observer can change substantially. The event appears dimmer. Its characteristic photon energies become lower. A burst that looks like a powerful gamma-ray burst to an observer near the jet axis may look softer to someone watching from outside the brightest part of the beam. That immediately suggests an explanation for X-ray flashes. Perhaps some of them are ordinary gamma-ray bursts seen from the side. This became one of the major ideas considered when astronomers were trying to understand why XRFs seem to form a continuum with classical GRBs. The simplest version imagines a jet with fairly uniform properties inside a particular opening angle and much less emission outside it. This is sometimes called a top hat jet. The name comes from the shape of the idealized energy distribution, not from the preferred clothing of collapsing stars. Inside the jet boundary, the energy per unit angle is roughly constant. Outside it, the energy drops sharply. An observer looking down the jet sees the bright, hard event. An observer outside that opening angle receives less strongly boosted radiation. The burst becomes fainter and softer. Move sufficiently far away from the jet axis and the prompt burst may become extremely difficult to detect at all. In that picture, a gamma-ray burst, an X-ray rich gamma-ray burst, and an X-ray flash might sometimes be the same type of explosion viewed from different angles. It is an elegant idea. It explains why the categories overlap. It makes use of relativistic physics we already know must be important, and it avoids requiring every soft burst to have a completely different central engine. Unfortunately, elegance does not guarantee that nature has signed the paperwork. When astronomers studied individual XRFs in detail, The simple off-axis explanation did not fit all of them. One of the clearest examples was XRF 060218. Its association with SN 2006AJ gave astronomers unusually detailed information about the explosion. Optical, X-ray and radio observations indicated that this event was genuinely less energetic than typical cosmological gamma-ray bursts. A 2006 study of the supernova and burst concluded that XRF 060218 was better explained as an intrinsically weak, soft event than as an ordinary classical GRB merely viewed away from its jet axis. That did not kill the viewing angle idea. It meant the idea was not the whole story. Some XRFs may indeed be produced or strongly influenced by viewing geometry. Others may be physically weaker explosions, and some may involve both effects. This is fairly typical of astronomy. A scientist proposes one explanation. The explanation works beautifully for several objects. Then another object appears and behaves as though it has not read the paper. A more realistic picture of a relativistic jet may also be more complicated than the top hat model. The jet might have structure. Instead of having the same energy everywhere inside one sharp boundary, it could contain an energetic core surrounded by slower or less energetic material. An observer looking close to the center would see the brightest and hardest radiation. Someone farther away might still see a burst, but the signal could be weaker and softer. There would be no single edge where the GRB suddenly stops existing. The properties would change gradually with viewing angle. That kind of structured jet fits naturally with the observation that XRFs, X-ray-rich bursts and classical gamma-ray bursts form a continuous distribution rather than three cleanly separated piles. Another possibility changes the jet itself rather than the observer. Relativistic jets are often described by something called the Lorentz factor. You do not need the equation to understand what it means. The Lorentz factor tells us how strongly relativistic the motion is. A Lorentz factor close to 1 describes material moving at speeds where ordinary Newtonian intuition still works reasonably well. A Lorentz factor of tens or hundreds describes material moving extraordinarily close to the speed of light. Gamma-ray burst jets can reach very high Lorentz factors. That fast motion is important because it affects how bright, hard, and rapidly varying the emission appears. Now imagine an explosion that launches a jet, but the jet does not accelerate quite as successfully. Perhaps too much ordinary matter becomes mixed into the outflow. Physicists often call this baryon loading. Baryons are particles such as protons and neutrons, the ordinary material making up most of the star. If a large amount of that matter becomes caught in the jet, the available energy has more mass to accelerate. The outflow may therefore achieve a lower Lorentz factor. This idea has sometimes been described using the wonderfully informal phrase, dirty fireball. The fireball contains too much material to reach the extreme relativistic speeds of the cleanest, fastest GRB jets. It can still be energetic, it can still produce high-energy radiation, but the characteristic emission may be softer. More of it may appear in X-rays rather than gamma rays. From a satellite near Earth, such an event might fall into the XRF category. At the opposite extreme, researchers have also considered very low baryon loading and different radiation conditions, because changing the composition, speed, magnetic field, and internal structure of an outflow can alter the spectrum in several ways. This is where the apparently simple question, why are there fewer gamma rays, begins producing a rather long answer. The prompt radiation from a GRB is itself not completely understood. Astronomers know a tremendous amount about these events, but the exact process that converts the kinetic and magnetic energy of a relativistic outflow into the observed gamma-ray spectrum is still an active subject of research. One long-standing idea involves internal shocks. Imagine the central engine launching several shells of material at different speeds. A slower shell leaves first, a faster one follows. Eventually the faster shell catches up, they collide. Part of their kinetic energy is converted into radiation. electrons can be accelerated to enormous energies and radiate through processes such as synchrotron emission in magnetic fields. Other models place greater importance on magnetic reconnection, where stored magnetic energy is rapidly converted into particle energy and radiation. Photospheric models focus on radiation escaping once the outflow becomes transparent enough for photons to get out. Real events may involve more than one process. So producing an X-ray flash could mean changing the jet speed, the magnetic conditions, the amount of matter in the outflow, the radius where energy is released, or the angle from which we observe it. A softer spectrum is the clue. It is not the mechanism. There is another useful measurement here called isotropic equivalent energy. The name sounds worse than the idea. Suppose you observe a GRB and calculate how much energy it would have released if it had radiated equally in every direction. That gives the isotropic equivalent energy. But if the radiation was actually concentrated into a narrow jet, the true energy can be much smaller than that number. Imagine shining a flashlight across a dark room. Someone standing inside the beam receives a bright signal. If they incorrectly assume the flashlight was radiating that same brightness equally in every direction, they would greatly overestimate the total power of the flashlight. Gamma-ray bursts create a much more extreme version of this problem. Their jets can make the apparent energy release look enormous. Once the jet opening angle is considered, the real energy budget changes. For XRFs, determining whether the lower apparent energy is caused by geometry or by an intrinsically weaker explosion becomes crucial. An off-axis GRB can look faint even when the underlying jet is powerful. A genuinely low-energy burst looks faint because the explosion really did place less energy into ultra-relativistic material. The two possibilities can initially resemble one another. Their later behaviour helps separate them. This is where afterglows become valuable again. As a relativistic jet moves outward, it sweeps up material from the surrounding environment. That gradually slows the jet. As its Lorentz factor decreases, the relativistic beaming becomes less extreme. Radiation that was previously concentrated into a narrow direction spreads over a wider apparent angle. Now consider an observer who started outside the central beam. During the prompt burst, that observer may see very little because most of the radiation is beamed elsewhere. But later, as the jet slows, the widening emission region may become visible. In some off-axis models, the afterglow should therefore brighten or evolve in a recognizable way, as the observer begins receiving more emission from the energetic jet. Radio telescopes are particularly useful for testing this. Radio emission can continue long after the initial X-ray or gamma-ray signal has faded. By following the radio source over time, astronomers can estimate the energy and speed of the expanding ejector. If an XRF was secretly a powerful classical GRB viewed from the side, researchers might eventually expect signs of a much more energetic jet to reveal themselves as that jet slows. For XRF 060218, radio observations did not reveal a hidden classical GRB jet carrying the usual enormous reservoir of relativistic energy. Instead, the event showed mildly relativistic ejecta with roughly 10 to the power of 48 ergs coupled to that fast material, far below the relativistic energy scale typical of powerful cosmological GRBs. The same study argued that the presence of relativistic ejecta separated XRF 060218 from ordinary Type 1bc supernovae, even though it was much less energetic than classical GRBs. That makes XRF 060218 especially useful. It sits between familiar categories. It was not an ordinary supernova. It had an engine. It produced fast ejecta. It generated a long, soft, high-energy transient. Yet it was not simply a standard, powerful GRB with most of the radiation aimed elsewhere. The supernova itself supported that interpretation. SN2-006AJ was a Type 1c supernova, but it was less luminous than the supernovae associated with some of the best-known classical long GRBs. Its ejecta velocities were also intermediate between ordinary supernovae and the more extreme GRB-associated explosions studied previously. So the quiet cousin was not merely standing farther away from the microphone. In this case, it really was speaking more softly. That raises an interesting population question. If some XRFs are intrinsically weaker than classical GRBs, we can only detect them across a smaller volume of the universe. A brilliant gamma-ray burst can be observed from enormous cosmological distances. A low-luminosity XRF becomes too faint to detect much sooner. That means the number we discover does not directly tell us how common they are. Imagine two kinds of lighthouse. One has an enormous lamp visible from hundreds of kilometers away. The other has a smaller lamp visible only nearby. If you count all the lighthouses you can see from one location, the powerful type will dominate your sample, even if the weaker type is actually much more common. Astronomy has this problem constantly. Bright things are easier to find. Rare bright things can therefore appear overrepresented compared with common faint things. In the case of XRF 060218, researchers estimated that low luminosity events of this general kind could occur considerably more often than powerful cosmological GRBs. The 2006 radio and X-ray analysis estimated a rate around 10 times higher for events similar to XRF 060218, although such estimates depend on small samples and assumptions about what counts as the same population. That possibility changes the way we think about stellar death. Classical GRBs are spectacular, but they may represent only the most visible end of a broader range of engine-driven explosions. Some stars may produce extremely successful relativistic jets. Some may produce weaker jets. Some jets may fail to escape. Some may emerge with modest relativistic energy. Some events may direct their brightest emission away from us. Others may produce significant soft X-ray radiation through shocks associated with the explosion. The sky could contain many more imperfect, weak or poorly aimed engines than the bright GRBs suggest. That would make sense. Nature rarely produces only the cleanest possible version of a process. Not every hurricane reaches the same strength. Not every volcanic eruption produces the same plume. Not every car engine leaving a factory performs identically after 15 years, although stellar astrophysics thankfully has fewer warranty departments. So why should every collapsing massive star capable of launching a jet produce the same jet? The progenitor stars differ. Their masses differ. Their rotation rates differ. Their metallicities differ. Their binary histories differ. Their envelopes differ. The central compact objects differ. The amount of matter continuing to fall onto those objects differs. The magnetic fields differ. The surrounding environments differ. A range of outcomes is not surprising. The interesting part is learning which physical differences correspond to which observed signals. One dying star produces an ordinary Type 1c supernova. Another produces a supernova and a low luminosity XRF. Another produces a brilliant long GRB and a broad-lined Type 1c supernova. Those may not be separate machines. They may be different operating conditions of related machines. XRFO 60218 added another complication because its X-ray spectrum contained evidence for a thermal component in addition to the usual non-thermal radiation. A thermal component behaves more like radiation associated with hot matter having a characteristic temperature. Researchers studying the event interpreted this component as possible evidence of a shock breaking out through dense material surrounding the progenitor star. That means the X-rays may have been telling us about more than the relativistic jet. They may also have been showing us part of the supernova shock itself reaching a region where radiation could escape. If that interpretation is correct, XRFO 60218 gave astronomers an unusually direct view of processes occurring during the transition from stellar collapse to visible supernova. A classical GRB can be so dominated by brilliant jet emission that other components are difficult to separate. A weaker XRF may give those components more room to become noticeable. Quiet can sometimes be useful. A person whispering in a silent room may be easier to understand than someone speaking during a fireworks display. This does not make XRF simple, it makes them valuable. They may reveal parts of stellar collapse that brighter gamma-ray bursts overwhelm. They can test whether relativistic jets form a continuous range of energies. They allow astronomers to search for weak central engines. They provide a way to compare ordinary supernovae with the most powerful engine-driven explosions. And they force us to separate three questions that initially look like one. How powerful was the engine? How effectively did that engine accelerate material? And from what angle did we observe the resulting outflow? A soft burst could come from a powerful engine viewed unfavourably. It could come from a weaker engine viewed directly. It could come from a jet that never reached the Lorentz factors of an ordinary GRB. It could contain radiation from shock breakout. It could involve a structured jet where there is no simple divide between on-axis and off-axis viewing. Different XRFs may answer those questions differently. That is why astronomers do not simply take the phrase X-ray flash and translate it into one specific picture of a dying star. The label describes the signal. The rest has to be reconstructed. And reconstruction becomes much easier when we stop treating the jet as an invisible line drawn from the centre of the star and start asking what that jet actually does while it moves. Once a jet begins near the centre of a collapsing star, it has not yet become the thing a satellite eventually detects. At first, it is trapped. The compact object at the centre may already be feeding enormous amounts of energy into the outflow, and material inside that outflow may already be moving at relativistic speeds, but there can still be thousands or tens of thousands of kilometres of stellar matter between the engine and open space. So the jet has to travel through the star. That sounds simple until we remember that the star is not hollow. The route ahead contains dense, hot material that is itself moving during the collapse and explosion. The jet cannot simply coast through it. It has to push that matter aside. This creates a useful distinction between the speed of the material inside the jet and the speed of the jet's leading edge. Material flowing through the jet can move extremely close to the speed of light. The head of the jet, however, is advancing into dense stellar gas and can move more slowly because it is constantly colliding with material in front of it. Imagine pushing a high-pressure hose through a pile of wet sand. The water leaving the hose may be moving quickly, but the front of the channel does not automatically move at the same speed. Energy is being spent clearing a path. A relativistic stellar jet is vastly more complicated, but the basic problem is similar. The jet keeps feeding energy toward its head. The head hits stellar material. A shock develops in front of it. The star's gas is heated and pushed sideways. The jet continues trying to advance. This interaction creates a region of hot material around the jet known as a cocoon. The word makes it sound comfortable. It is not. The cocoon contains shocked material from both the jet and the surrounding star. It can become extremely hot and pressurized as the jet drills outward. NASA descriptions of long GRBs show the jet boring through the collapsing star along its rotation axis, while simulations and observations of some long events indicate that shocked stellar gas can flow around the jet and form a hot sheath or cocoon. That pressure can actually help the jet. The cocoon surrounding it squeezes the outflow from the sides, helping keep it narrow. This is called collimation. Instead of expanding freely in every direction, the jet is confined into a tighter channel as it crosses the star. So there is an odd partnership taking place. The star is the obstacle the jet must escape. At the same time, the pressure created by that obstacle helps shape the jet into the narrow structure that may eventually produce a gamma-ray burst. The important question is whether the engine can keep going long enough. A jet cannot live on momentum alone indefinitely. The central engine has to continue feeding energy into it while the head works its way toward the surface. Suppose the engine stays active. The jet head advances. The stellar material above it becomes thinner. Eventually, the jet reaches the outer edge of the star. At that moment, the situation changes rapidly. The jet is no longer pushing through the dense interior. it breaks into the much lower density environment surrounding the star. The pressure holding everything tightly confined begins to change. The jet can accelerate and expand. The cocoon can also escape. Material that spent its journey trapped around the jet suddenly has room to spread outward. That is jet breakout. For a successful long gamma-ray burst, breakout is an important threshold. Before breakout, most of the central engine's activity is hidden inside the star. After breakout, relativistic material can travel outward through space, and radiation associated with the jet becomes much easier to observe. But success is not guaranteed. If the engine shuts down before the jet reaches the surface, the jet may stall. The remaining energy can still affect the explosion. The hot cocoon can contribute to pushing stellar material outward. There may still be a supernova, there may still be X-ray or other high-energy emission, but the event will not necessarily produce the bright classical gamma-ray burst expected from a successful ultra-relativistic jet. NASA has used the term fizzle when describing GRB2 00826A, an unusually short burst linked to a collapsing massive star. One interpretation was that its jets only barely lasted long enough to break through the stellar surface before the engine shut down. Had they been slightly weaker or shorter-lived, the recognizable gamma-ray burst might not have occurred at all. That example is useful because it shows how sensitive the final signal can be to timing. The difference between a jet that escapes and one that fails may depend on the competition between two clocks. How long does the jet need to cross the star, and how long does the central engine remain active? If the engine runs longer than the breakout time, the jet can emerge while energy is still flowing into it. If the engine stops too early, the jet can be buried. Change the size of the star and you change how far the jet has to travel. Change the density of the stellar envelope and you change how difficult that journey is. Change the jet power and you change how quickly the head can advance. This is one reason stripped massive stars are so important in ordinary long GRB models. A compact star that has already lost its extended hydrogen envelope gives the jet a shorter route to the surface. A large supergiant provides a much longer route. For extremely long bursts, researchers have even considered progenitors with extended envelopes, because a jet moving through a much larger star could remain involved with stellar material for far longer than in the usual compact Wolf-Rayet picture. Once the jet escapes, another problem begins. Now astronomers have to explain how the energy carried by the outflow becomes X-rays and gamma rays. A relativistic jet contains enormous kinetic energy, but fast-moving material is not automatically a gamma-ray burst. There needs to be a way to convert some of that bulk motion into radiation. This remains one of the major open areas in GRB physics. The broad picture is well established. A compact engine launches an ultra-relativistic outflow. Energy is dissipated within that outflow. Particles are accelerated, radiation is produced. What is still debated is exactly where the most important dissipation happens and which physical process dominates in different bursts. One possible source of radiation appears surprisingly early. Near the central engine, the jet is so dense that photons cannot easily escape. The outflow is opaque. Photons scatter repeatedly from charged particles instead of simply travelling outward. As the jet expands, its density falls. Eventually it reaches a region where photons can begin escaping efficiently. That region is called the photosphere. The name is borrowed from stars. The Sun has a photosphere, which is roughly the layer from which most of the visible light we receive can escape. A GRB jet can also have a photosphere, although the conditions are obviously rather different from a pleasant afternoon in sunlight. Radiation escaping from the jet photosphere may produce a thermal or quasi-thermal component in the observed spectrum. Researchers have found evidence for such components in some gamma-ray bursts, although their importance varies from event to event. Reviews of GRB prompt emission note that photospheric components can sometimes be visible beneath or alongside a broader non-thermal spectrum. Above the photosphere, the jet becomes transparent enough that radiation produced farther out can escape more directly. Now imagine that the central engine is not perfectly steady. For a few moments it launches material at one speed, then it produces a faster shell, then another slower one. The jet becomes a stream of relativistic material with different parts moving at different velocities. Eventually, faster material can catch slower material. When that happens, shocks form inside the jet. These are called internal shocks. A collision between two relativistic shells does not resemble two cars bumping into one another. The shells are made of plasma. Magnetic fields are present. Particles can be accelerated to extreme energies. A forward shock travels into the slower material ahead, while a reverse shock moves back through the faster material behind. Part of the ordered kinetic energy of the flow becomes disordered particle energy and radiation. Internal shocks remain one important model for producing the rapidly varying prompt emission of gamma-ray bursts. Recent work continues to show that collisions between faster and slower relativistic shells can produce forward and reverse shocks whose synchrotron emission reproduces important features of observed GRB pulses and spectra. This picture also provides a natural reason gamma-ray burst-like curves can look so complicated. Some bursts do not produce one smooth pulse, they produce several. A bright spike appears, then another, then perhaps a weaker pulse, then activity returns. If the central engine is variable, the jet can preserve some record of that behaviour. Different shells collide at different times and distances from the star. Each collision can contribute another pulse. So when a detector records a jagged burst lasting several tens of seconds, it may be seeing the consequences of an engine that was repeatedly changing while material was being launched. The light curve becomes an indirect record of activity occurring near a compact object far too small and distant for us to image directly. Internal shocks are not the only option. The jet may contain a great deal of magnetic energy. If magnetic fields carry a large fraction of the energy, magnetic reconnection could become important. Magnetic reconnection occurs when magnetic field structures rearrange in a way that rapidly converts stored magnetic energy into particle motion and heat. The process happens in other astrophysical environments too, including the Sun. In a GRB jet, the available energies are considerably larger. A magnetically dominated outflow could dissipate energy through reconnection rather than relying mainly on collisions between shells. Some models combine several mechanisms. Photospheric emission may contribute at lower energies. Synchrotron radiation from accelerated particles may dominate much of the broader spectrum. Additional scattering processes can modify the photons. The exact mixture can differ from one burst to another. That uncertainty becomes particularly relevant for X-ray flashes. If the characteristic energy of the radiation depends on how efficiently the jet accelerates, how strong its magnetic field is, where energy is dissipated, how fast the material moves, and what part of the outflow we see, then there are several ways to shift the observed spectrum downward. Consider particle acceleration. A shock can accelerate electrons to relativistic speeds. Those electrons move through magnetic fields. Charged particles moving through magnetic fields can emit synchrotron radiation. The characteristic frequency of that radiation depends on the energy of the electrons, the strength of the magnetic field, and the relativistic motion of the emitting region. Change those ingredients and the spectral peak changes. A very fast jet with energetic electrons and strong boosting toward Earth can produce photons at gamma-ray energies. A slower or less strongly boosted outflow may move the characteristic radiation toward X-rays. This does not require the jet to stop being relativistic. It only requires different conditions. Relativity is not an on and off switch. Material can move at 90% of the speed of light, 99%, 99.9%, or even closer. Those differences may sound small when expressed as percentages, but the corresponding Lorentz factors and observational effects can differ substantially. This is why the speed of the outflow matters so much. A jet with a Lorentz factor of several hundred behaves very differently from material that is only mildly relativistic. The beaming is stronger, the Doppler boosting is stronger, the photons we receive can appear more energetic, the timescales can appear compressed, so an XRF may sometimes be showing us an outflow that never reached the extreme Lorentz factors of a classical GRB. Perhaps the jet contained more ordinary stellar material. Perhaps it had to work harder while crossing the star. Perhaps the engine supplied less energy. Perhaps we are seeing slower material surrounding a faster core. Or perhaps the fastest material exists, but is pointed somewhere else. The cocoon becomes especially interesting here. As the jet drills through the star, energy deposited around it does not simply vanish. The cocoon can emerge when the jet reaches the surface. Unlike the narrow central jet, cocoon material can spread across a much wider range of angles. It may also move more slowly. That makes its radiation softer and less strongly beamed. An observer who is not looking directly into the jet could still receive emission from the cocoon. In some events, this kind of wider angle component may contribute to X-rays even when the hardest gamma ray emission is aimed elsewhere. This provides another way to understand why the boundary between GRBs and XRFs can become complicated. There may be several emitting regions, a narrow ultra-relativistic core, slower material around that core, a hot cocoon, the supernova ejector, a shock moving through gas around the star. Each region has its own speed, temperature, magnetic field, and geometry. The detector near Earth receives the sum of whatever radiation happens to reach it. Then astronomers try to separate the ingredients. There is also an important difference between jet breakout and supernova shock breakout. The names sound similar, so they're easy to mix up. Jet breakout happens when the narrow relativistic jet reaches and escapes from the stellar surface. Supernova shock breakout happens when the broader shock produced by the exploding star reaches a region where trapped radiation can finally escape. These processes can occur in the same general event, but they are not identical. The supernova shock affects a much larger fraction of the star. As that shock approaches the surface, the material ahead of it becomes progressively less dense. Eventually, photons trapped behind the shock can diffuse outward faster than the shock is carrying them. A brief burst of radiation escapes. Depending on the progenitor star and its environment, that breakout emission may occur strongly in ultraviolet or X-ray wavelengths. If the star is surrounded by dense material that it expelled before dying, the effective breakout can happen in that surrounding gas instead of precisely at the visible surface. This became especially interesting in XRF 060218. Its long-lasting soft X-ray emission included a thermal component, and one influential interpretation connected that component with shock breakout associated with SN 2006AJ. The event was unusual enough that astronomers have continued debating the detailed origin of its different spectral components, so it is better to treat shock breakout as an important interpretation rather than a universally settled explanation for all XRFs. Either way, XRF 060218 demonstrated that a soft high-energy transient can contain information about more than a single narrow jet. The explosion as a whole matters. After the prompt emission, the jet continues moving outward. By now, the star itself is behind it. Ahead lies material surrounding the progenitor. That environment is not completely empty. The star may have spent thousands or millions of years losing matter through stellar winds. There may be gas in the region where the star formed. As the relativistic ejector sweep into that material, another shock develops. This is the external shock. The forward part of the outflow plows into the surrounding gas. The swept-up material is heated and accelerated. Electrons again interact with magnetic fields and produce radiation. Unlike the internal shocks associated with the brief prompt burst, the external shock can continue producing detectable emission for much longer. This is one of the main sources of the afterglow. NASA's descriptions of GRB emissions summarize this sequence well. Radiation can arise near the newborn black hole from internal collisions among fast-moving parts of the jet, and later from the leading edge of the jet as it sweeps through surrounding matter. The afterglow can begin in X-rays and extend through visible light and radio wavelengths. As the shock expands and slows, its emission evolves. High-energy radiation usually fades first. Lower-frequency emission can remain detectable much longer. For astronomers, this fading signal is extremely useful because the original flash is already over. The afterglow provides time, and time is something transient astronomy rarely gives away generously. During the prompt phase, everything can happen before a human has even seen the alert. The spacecraft detects the burst. Software decides whether it is significant. A location is calculated. The alert is transmitted. By the time an astronomer reads the message, the photons that triggered the entire event may have stopped arriving. The external shock does not disappear so quickly. Its afterglow can be studied for hours, days, weeks, or longer. From that fading light, researchers can estimate how energetic the outflow was, how the surrounding environment behaves, and whether the geometry looks like a narrow jet. That information becomes especially important when an XRF could be either a weak explosion or a powerful explosion seen from an unfavourable angle. Prompt emission alone may not tell us which one occurred. The later shock can. Suppose a powerful jet exists but is pointed somewhat away from Earth. At first, relativistic beaming directs most of its radiation elsewhere. As the jet sweeps up surrounding material, it slows. The beaming becomes less extreme. A wider region becomes visible. An off-axis observer may eventually see the afterglow brighten or change behaviour. If no hidden energetic jet appears, an intrinsically weak explosion becomes a more plausible explanation. So the shock is doing more than producing additional light. It is revealing the energy budget. The same is true of radio emission. Radio wavelengths can trace expanding ejecta long after the initial event. By measuring how the radio brightness changes, astronomers can estimate the speed and energy of the material. A burst that looked modest in X-rays might still reveal enormous kinetic energy later. Or it might remain modest, confirming that the relativistic component really was weak. This is how scientists turn a few seconds of radiation into a physical model. The X-rays tell us something. The gamma rays tell us something else. The optical light from a supernova adds another piece. Radio observations test the ejecta. Spectra give velocities and temperatures. Timing links the pieces together. No single measurement has to carry the entire explanation. That is useful because the journey from the stellar core to our detector contains too many places where the signal can change. The engine varies, the jet crosses the star, the cocoon forms, the jet breaks out, the photosphere becomes transparent, shells collide, magnetic energy dissipates, particles radiate, the outflow hits the surrounding gas, then the photons travel across intergalactic space, before finally reaching a small instrument orbiting a small planet. By that point, most of the explosion is already ancient history. The detector sees only what survived the journey and happened to fall inside its energy range. A classical GRB may send a hard, bright signal into the detector. An XRF may arrive with its energy concentrated lower in the spectrum. Those two signals may come from different engines. They may come from different jet speeds. They may come from different viewing angles. They may contain different contributions from the jet, cocoon, photosphere, or breakout shock. In some cases, several of those differences may be operating together. That is why there is no single diagram that explains every X-ray flash. There is a collection of physical processes, all beginning with a catastrophic stellar collapse, and all capable of altering the radiation before it reaches us. The encouraging part is that each process leaves clues. A photospheric component has a different spectral shape from ordinary synchrotron radiation. A shock breakout develops on timescales related to the star and surrounding material. A variable engine can create complex prompt pulses. An off-axis jet affects later afterglow behavior. A weak jet leaves a different energy signature in radio observations. The light may arrive all at once on a detector screen, but it carries information about where it came from. The difficulty is catching enough of that information before it disappears. An X-ray flash can erupt without warning in a patch of sky nobody was examining carefully a moment earlier. Its brightest phase may last less time than it takes to make a cup of tea. Ground-based telescopes cannot see X-rays from space directly because Earth's atmosphere absorbs them. The source may be billions of light-years away. What does it take to find these events, calculate their positions, alert observatories around the world, and begin tracking their fading afterglows before the most important photons are gone? The first requirement is simple enough to describe and surprisingly difficult to achieve. You have to be looking before the flash happens. An X-ray flash does not send an appointment request. There is no warning that a massive star in a distant galaxy is about to collapse, launch an outflow, and briefly become one of the brightest X-ray sources in the sky. The event can begin at any time and appear from almost any direction. That immediately makes ordinary astronomy rather inconvenient. Many telescopes have narrow fields of view. They point toward one selected object and study it carefully. That works beautifully when you already know where your target is. A galaxy is not going anywhere quickly. A star cluster will usually remain where you left it. A planet can be predicted. An X-ray flash is different. The telescope does not know where to point because the event has not happened yet. So the first instruments in the detection chain need to watch large areas of sky at once. That creates a trade-off. A wide-field instrument can notice sudden events across a large region, but it usually cannot study each source with the same detail as a narrow-field telescope. A narrow-field telescope can obtain much more precise measurements, but only after someone tells it where to look. This is why transient astronomy often works like a relay race. One instrument notices something, another determines a better position, other observatories begin detailed follow-up. The process has to happen quickly, because the source is already changing while the message is being sent. X-ray flashes made this especially clear during the era of Beper-Sachs and HETI-2. HETI-2 was built to monitor bursts across several high-energy bands at the same time. It carried gamma-ray detectors, a wide-field X-ray monitor, and soft X-ray cameras. Its onboard systems could recognize a burst, calculate a position, and transmit coordinates while the event was still recent enough for other telescopes to respond. For some bursts, those onboard positions could be calculated within tens of seconds. That may sound fast. For a transient astronomer, tens of seconds can feel surprisingly long. By the time someone receives an alert, finds the coordinates, checks whether the source is visible from their observatory, moves a telescope, takes an exposure, and confirms that they are looking at the correct object, the initial high-energy flash may already be finished. So much of the work has to be automated. The satellite watches the sky continuously. Its detector records a stream of events. Most of them are not distant stars dying. There is background radiation. There are known X-ray sources. There are charged particles striking the detector. There can be solar activity. There can be instrumental effects. There can be statistical fluctuations that briefly look interesting simply because large amounts of data occasionally produce something unusual. The onboard software therefore has to ask whether the incoming signal looks like a real astrophysical transient. One basic method is to monitor the count rate. A detector normally receives some background level of radiation. If the number of recorded photons suddenly rises significantly above that expected background, the software can flag the increase. But that alone is not enough. A detector cannot trigger every time the count rate changes slightly, or astronomers would spend much of their working lives responding to false alarms. The system compares the increase with expected statistical variations. It may examine different timescales. A very short burst could appear as a sudden spike lasting less than a second. Another transient may build over several seconds. An XRF can continue for tens of seconds or minutes. So the software searches in more than one time window. A burst that is obvious when counts are accumulated over 20 seconds might look insignificant in a 1 second window. The reverse can also happen. Then there is the question of energy. A classical gamma-ray burst may create a strong increase in a gamma-sensitive detector. A very soft X-ray flash may not. That is why broad energy coverage matters. HETE2's wide-field X-ray monitor was sensitive in roughly the 2 to 25 kilo-electron-volt range, helping it detect softer events that might have been far less impressive in a harder gamma-ray instrument. This is one of the reasons XRFs became recognizable as a population in the first place. The instruments had finally become good enough at looking in the right energy range. Once a burst has been detected, astronomers need to know where it came from. For many high-energy detectors, producing an image is not as straightforward as it is with an ordinary optical camera. Visible light telescopes can use mirrors and lenses to focus photons onto a detector. X-rays are more difficult. A normal mirror placed directly in front of an X-ray beam does not reflect those photons the way a bathroom mirror reflects visible light. At high energies, the radiation tends to penetrate or be absorbed by the material. Focusing X-ray telescopes solve this by using grazing incidence mirrors. Instead of hitting the reflective surface nearly head-on, the X-rays strike at very shallow angles and are guided toward a detector. These systems can produce detailed X-ray images. The problem is that they usually have relatively narrow fields of view. That is excellent once you know where the burst is. It is less useful when the burst could happen anywhere. Wide-field burst monitors often use a different technique. One common approach is the coded mask. Picture a patterned sheet containing opaque and open sections positioned above a detector. X-rays arriving from a particular direction pass through the open areas and cast a pattern onto the detector below. The pattern depends on the direction of the incoming radiation. Software compares the recorded pattern with the known mask design and reconstructs where the source must have been. It is something like identifying the position of a lamp by looking at the shadow it casts through a complicated window screen. Except the window screen was carefully designed by engineers, the lamp may be billions of light years away, and nobody's allowed to move anything by hand. Swift's Burst Alert Telescope, usually called BAT, uses coded aperture imaging for exactly this kind of wide-field monitoring. BAT surveys a large region of sky for sudden high-energy transients. When it detects a likely gamma-ray burst, it can calculate a source position and trigger the spacecraft to turn toward that location. Now the relay begins moving very quickly. Swift carries 2 narrower field instruments in addition to BAT. The X-ray telescope, or XRT, studies the source at X-ray wavelengths with far better localization. The ultraviolet/optical telescope, UVOT, searches for emission at ultraviolet and visible wavelengths. The spacecraft was designed so that after BAT detects a burst, Swift can autonomously slew toward the source, often within roughly a minute or two. The important word there is autonomously. The spacecraft does not wait for an astronomer to wake up, read an email, put on glasses, find coffee, and approve the maneuver. That would be far too slow. The satellite handles the immediate response itself. The BAT trigger provides an initial location. Swift begins turning. Then XRT and UVOT are placed on the source. Swift's nominal observing sequence was designed around slew shorter than about 90 seconds, with XRT and UVOT capable of beginning observations while the burst itself was still active in a fraction of cases. This is a remarkable piece of engineering when you think about what is happening. A spacecraft is orbiting Earth. A detector notices an unexpected flash from deep space. Software decides that the signal looks interesting. A position is calculated. The entire spacecraft changes orientation. A focusing X-ray telescope begins examining the same location. All of that can happen before most people would have found the correct telescope control manual. The XRT position is much more precise than the original wide-field trigger. That precision matters because the rest of the sky is crowded. A large error region may contain thousands of ordinary stars and many galaxies. Telling an optical astronomer that something exploded somewhere in this general area is useful, but only up to a point. A smaller error region greatly improves the chances of finding the correct fading counterpart. This localization problem becomes even more obvious when we look at instruments designed to watch huge portions of the sky. NASA's Fermi Gamma Ray Space Telescope carries the Gamma Ray Burst Monitor, or GBM. GBM watches a very large fraction of the unobscured sky and is excellent at detecting sudden high-energy events. Its detectors surround the spacecraft at different orientations. When a burst occurs, each detector sees a different signal strength depending on the direction of the source. By comparing those relative count rates, the system can estimate where the burst came from. The advantage is enormous sky coverage. The disadvantage is that the initial location can cover a much larger patch of sky than a focused X-ray position. That may be perfectly adequate for alerting other high-energy instruments. For an optical telescope with a small field of view, however, searching a region several degrees across can become a major task. To appreciate the scale, the full moon is about half a degree wide. An uncertainty region several degrees across can therefore cover an area containing many full moon-sized patches of sky. Some telescopes can search large regions quickly, others cannot. This is why burst localization is almost as important as burst detection. Knowing that an explosion occurred is only the beginning. To learn what exploded, astronomers need an address. The speed of communicating that address has also transformed transient astronomy. When high-energy satellites detect bursts, alert networks distribute information rapidly to observatories and researchers. Coordinates can reach robotic telescopes that are programmed to respond automatically. Those telescopes may interrupt whatever they were observing, move to the burst position, and begin taking images without waiting for a human operator. The universe has interrupted the schedule. The telescope accepts this more calmly than most people would. A robotic optical telescope might take an image minutes after the high-energy trigger. Another observatory could begin infrared observations. Radio telescopes may join later. Large optical telescopes can obtain spectra if the counterpart is bright enough. Space-based X-ray observations continue tracking the source. The original flash has now become a coordinated international observing campaign. Different parts of Earth also matter. Suppose the burst occurs in a part of the sky visible from Australia but below the horizon in Europe. An Australian telescope may begin immediately. Hours later, as Earth rotates, observatories elsewhere can take over. This is particularly useful because afterglows evolve continuously. The first measurements tell researchers what happens minutes after the burst. Later observations show the source after hours, then days, then weeks. A global network can therefore build a much more complete picture than one observatory could manage alone. Weather adds its own contribution to the problem. An alert may arrive with beautiful coordinates and excellent timing. The telescope may be available. The source may be above the horizon. Then there are clouds. Astronomy is a profession in which billions of years of cosmic history can occasionally be defeated by local rain. Space telescopes do not have that particular problem, but they have others. Earth can block the target. A spacecraft may pass through regions where detectors have to be protected from high particle backgrounds. The sun can make some directions unsafe to observe. The moon can interfere with certain instruments. Operational constraints determine whether a follow-up can happen immediately. No single observatory can do everything. That is why having multiple instruments matters. For an X-ray flash, the first challenge is often that the signal is soft. A detector optimized mainly for high-energy gamma rays might register only part of it. A softer X-ray monitor may see it much more strongly. Comparing measurements from several instruments helps reveal the true spectrum. Perhaps one satellite records a clear X-ray transient. Another sees weak gamma ray emission at the same time. A third instrument sees nothing because the event falls below its sensitivity. Those are all useful results. Even a non-detection can place limits on how much radiation was present in a particular energy range. That is how astronomers determine that the spectrum was genuinely soft rather than simply faint. Timing also allows detectors separated by large distances to help locate bursts. If the same high-energy transient reaches spacecraft at different positions in the solar system, the photons will arrive at slightly different times. The difference may be tiny. But light moves at known speed. If astronomers know where the spacecraft were, the arrival time differences can restrict the direction from which the signal came. This is the basic principle behind the interplanetary network, which has used high-energy detectors on multiple spacecraft to triangulate gamma-ray bursts. Imagine hearing a loud noise with several microphones spread across a large field. The microphone nearest the source receives the sound first, the others receive it slightly later. Measure those differences precisely enough, and you can work backward toward the source direction. For cosmic bursts, the microphones are spacecraft and the signal moves at the speed of light rather than the speed of sound. The distances between detectors can be enormous. That gives the timing measurement substantial geometric leverage. Still, rapid localization is only part of the problem. Astronomers also need to decide what kind of event triggered the detector. Not every high-energy flash is an XRF or GRB. There are bursts from magnetars in our own galaxy. There are X-ray binaries. There are solar flares. There are particle events. There are active galactic nuclei that can vary. Different transients occupy different timescales, spectra, sky locations, and patterns of repeated activity. A GRB-like event tends to appear once from a particular distant source and fade. A repeating source immediately suggests a different explanation. The spectral shape provides another clue. Duration helps. The location relative to the galactic plane helps. Finding an afterglow helps enormously. And eventually identifying a host galaxy can settle the question of whether the source lies inside our galaxy or far beyond it. This is why those first minutes after detection matter so much. Suppose an X-ray flash lasts 100 seconds. During those 100 seconds, the prompt emission may change rapidly. The spectrum can evolve. The peak energy can shift. Individual pulses can rise and fall. If the detector has sufficient time resolution, astronomers can examine these changes almost photon by photon. Then the prompt signal ends. The source may still be bright in X-rays, but the emission is now entering a different phase. A few minutes later, the X-ray flux may already be much lower. An optical counterpart may be fading. Every delayed observation loses access to part of the early behavior. Before rapid response satellites, astronomers often began follow-up long after the burst. They could study the later afterglow but had missed the transition from prompt emission into the early X-ray phase. Swift changed that dramatically by moving quickly enough to observe very early afterglows, and those observations revealed that the early X-ray behavior of GRBs was often much more complicated than a simple smooth decline. Some afterglows fell extremely rapidly. Some entered flatter periods called plateaus. Some suddenly brightened again in X-ray flares. Some showed evidence that the central engine was continuing to affect the event long after the main prompt gamma-ray emission had ended. That was a surprise. The old simple picture imagined a central engine producing the initial burst and then switching off while the expanding blast wave generated a gradually fading afterglow. Swift showed that at least some bursts refused to be that well behaved. The source can continue producing internal activity. Energy can be injected into the blast wave. Late shells can catch earlier material. X-ray flares can appear hundreds or thousands of seconds after the original trigger. For XRFs, this early behavior can be particularly valuable because the prompt signal is already concentrated in the X-ray band. The distinction between the end of the prompt phase and the beginning of the afterglow may not always be obvious. One component fades, while another begins contributing. Thermal emission may appear, jet-related emission may continue. The external shock becomes increasingly important. The light curve can therefore contain overlapping processes. This is why a telescope that responds in 100 seconds can tell us something very different from one that arrives 3 hours later. Both observations matter. They are simply looking at different stages. Spectroscopy becomes important too. A detector does not only measure whether the source is bright, it measures how brightness changes with photon energy. take the incoming X-rays and divide them into energy bins. Perhaps the source produces many photons around a few kilo-electron volts and fewer at higher energies. Perhaps the spectrum changes as the event fades. Perhaps absorption by material between the source and Earth removes some lower energy photons. Perhaps there is an additional thermal component. Each possibility alters the spectrum. The challenge is that the source is fading while you measure it. Early on, there may be enough photons to obtain a detailed spectrum over short intervals. Later, the telescope may need to collect photons for much longer before there are enough to analyse. The better the localization becomes, the easier it is to connect the transient with objects seen at other wavelengths. An optical telescope might find a fading point source inside the X-ray error region. That source can then be monitored. If it continues fading, confidence grows that it is the afterglow. A spectrum might reveal absorption or emission lines that provide the redshift. Now, astronomers know the distance scale. Knowing the distance changes everything. A faint nearby event and a faint distant event do not represent the same physical explosion. With a redshift, the observed brightness can be translated into an estimate of luminosity or energy. The observed photon energies can be corrected into the source's rest frame. The duration can be corrected for cosmological time dilation. The soft burst that looked unusual in the detector can now be compared physically with other XRFs and GRBs. Later, another signal may emerge. The optical afterglow keeps fading. But instead of continuing smoothly downward, the source begins to show extra light. Over several days, a supernova becomes visible. Now the burst has a stellar identity. This is what made events such as XRF 060218 so valuable. Swift detected the high-energy transient and followed it rapidly in X-rays and ultraviolet light, while ground-based observatories studied the associated supernova SN2006AJ. The event could be followed from the initial X-ray emission into the expanding stellar explosion. Without rapid localization, that connection would have been much harder to establish. And there is something slightly remarkable about the entire process. The star itself does not know any of this is happening. The explosion occurred long before the alert reached Earth. The photons arrive, a detector registers them, software recognizes a change, a spacecraft turns, coordinates are distributed, robotic telescopes respond. Astronomers begin measuring a source that may already have changed several times since the first trigger. For the event, everything happened naturally. For us, catching it requires satellites, coded masks, grazing incidence mirrors, onboard computers, communications networks, automated telescope schedules, precise clocks, and many researchers trying to understand the same fading dot before it becomes too faint. The original X-ray flash may last only minutes. The investigation begins during those minutes but does not end with them. In fact, some of the most useful information arrives after the dramatic part is over. The first clue left behind is usually not another explosion. It is a fading source. The intense prompt emission has ended. The detector that triggered the alert is no longer seeing the same rush of high-energy photons, and yet the location does not immediately become quiet. X-rays continue arriving. Optical light may appear. Radio emission may become detectable later. The source gets weaker, but that weakening is exactly what astronomers want to measure. Because the afterglow is not simply leftover light from the flash, it is a new stage of the event. By the time the afterglow dominates, fast-moving ejecta from the explosion are interacting with material surrounding the dead star. The relativistic outflow sweeps gas ahead of it, slows down, forms shocks, accelerates particles, and produces radiation across a wide range of wavelengths. The central flash told astronomers that something happened. The afterglow begins telling them what was thrown outward when it happened. Imagine the jet leaving the star at an enormous speed. At first, it has so much momentum that the thin gas around the progenitor barely slows it. But space around a massive star is not completely empty. The star may have spent much of its life losing material through stellar winds. its surrounding region can contain gas shaped by that earlier mass loss. The expanding outflow begins gathering that material. One atom makes almost no difference. Neither does a million. Eventually, however, enough mass has been swept up that the jet can no longer ignore it. The outflow begins transferring energy into the surrounding gas. A forward shock moves outward into the environment. Behind that shock, particles are heated and accelerated. Magnetic fields become amplified. Electrons moving through those magnetic fields produce synchrotron radiation, one of the main processes used to explain GRB afterglows. Synchrotron radiation is not unique to gamma-ray bursts. It appears throughout astrophysics whenever charged particles move relativistically through magnetic fields. The interesting part here is its range. The same expanding shock can produce emission detectable in X-rays, visible light, infrared, and radio wavelengths, with different parts of the spectrum evolving at different rates. So astronomers are no longer studying one flash in one energy band. They are watching an expanding physical system, and the way that system fades contains information about its energy, speed, geometry, and environment. Suppose the X-ray brightness declines smoothly as a power law. That means it does not lose the same amount of brightness every hour. Instead, its decline follows a mathematical relationship between brightness and time. This kind of fading is expected when an expanding relativistic blast wave is gradually decelerating. The exact slope of the decline depends on several things, including how energetic the electrons are, how the surrounding material is distributed, and which part of the synchrotron spectrum the telescope is observing. Astronomers can compare the observed decline with theoretical models. Does the environment look roughly uniform? Or does its density decrease with distance in the way expected around a star that has been blowing a strong wind? Does the X-ray spectrum agree with the optical spectrum? Does one band fade faster than another? Did a characteristic frequency pass through one observing band? Each answer removes some possibilities. That is what makes a fading source useful. A bright prompt burst can be complicated because the central engine may still be active. Different shells can collide. Magnetic structures can reconnect. Several radiation processes can operate at once. The later afterglow can be simpler. Not always simple, just simpler, which is a valuable distinction in astrophysics. The outflow is now interacting with its environment in a way that can often be modelled using shock physics. One useful concept is the cooling frequency. The electrons accelerated by the shock do not keep their energy forever. They lose energy by radiating. Very energetic electrons cool more rapidly than less energetic ones. This creates a characteristic point in the synchrotron spectrum separating electrons that have had time to cool substantially from those that have not. As the blast wave evolves, that cooling frequency can move through different observing bands. When it does, the spectrum and fading rate can change in predictable ways. There are other characteristic frequencies too. One is associated with the typical energy of newly accelerated electrons. Another marks the low-frequency region, where the emitting material can absorb some of its own synchrotron radiation. The complete spectrum therefore changes as the blast wave expands. X-ray telescopes see one part, optical telescopes see another, radio telescopes see another. Putting those observations together is rather like having several cameras pointed at different pieces of the same machine. One camera shows the wheels, another shows the engine, another shows the exhaust. None gives the whole answer, but together they reveal much more than any one view. The fading rate can also expose the shape of the outflow. Early in a GRB, a narrow relativistic jet can behave observationally, as though it were part of a much larger spherical explosion. That happens because relativistic beaming allows us to see only a small region around the material moving almost directly toward us. The rest of the jet is outside our effective view. As the outflow slows, the beaming becomes less severe. A larger portion of the jet becomes visible. Eventually, the observer begins to notice that the explosion is not spherical. Under some conditions, that produces a change in the rate at which the afterglow fades. Astronomers call this a jet break. Before the break, the light curve follows one decline. Afterward, it becomes steeper. If the interpretation is correct, the timing of that change can help estimate the opening angle of the jet. And once the opening angle is known, researchers can make a better estimate of the true energy of the explosion. This matters because the apparent energy of a GRB can be misleading. If you assume the burst radiated equally in every direction, the calculated energy can be extraordinary. If the radiation was actually concentrated into a narrow jet, the real total energy can be substantially lower. For X-ray flashes, jet geometry becomes even more interesting because viewing angle may help explain why some events appear soft. Imagine a powerful jet aimed slightly away from Earth. During the prompt phase, the hardest and brightest radiation is strongly beamed away from us. We may see a weak, soft transient. At first, that could resemble an intrinsically weak XRF. But the jet does not remain ultra-relativistic forever. As it hits surrounding material, it slows. Its radiation becomes visible over a wider angle. If Earth was sitting outside the original beam, the afterglow may become brighter as more of the energetic jet enters our view. This gives astronomers a test: a soft prompt flash, followed by the later appearance of a powerful afterglow, could support an off-axis interpretation. A soft flash followed by an afterglow that remains weak may suggest something else. Perhaps there was no hidden classical GRB jet. Perhaps the event was intrinsically less energetic from the beginning. Radio observations are particularly good at checking this. Radio afterglows can last much longer than the initial X-ray signal. By the time the ejecta have slowed substantially, the extreme relativistic beaming that complicated the prompt phase is less important. The radio source can therefore provide a more direct estimate of how much kinetic energy was carried by the fast material. This is sometimes described as calorimetry, not because anyone is counting the nutritional value of a supernova. The idea is that the expanding shock acts as a record of the energy that was placed into the ejecta. Measure how the radio source evolves, model the interaction with the surrounding gas, and you can estimate how much energy the explosion deposited into fast-moving material. That test was especially important for XRF 60218. If the event had been a normal, powerful GRB whose jet simply missed Earth, astronomers might have expected later observations to reveal a much larger reservoir of energetic relativistic ejecta. The radio observations did not support that simple picture. Instead, XRF 60218 appeared genuinely sub-energetic compared with classical cosmological GRBs. Its associated supernova SN2006AJ was also less luminous than several famous GRB-associated supernovae, and its ejecta velocities sat between those of ordinary Type 1c supernova and the more extreme GRB supernova events. The flash and the supernova were both pointing in a similar direction. This stellar death really did seem to be less extreme than the brightest GRB-producing explosions. Not harmless, not ordinary, just less powerful. And that distinction helps explain what we mean when we ask why some stellar deaths whisper instead of roar. There is probably no single answer. One possibility is that the central engine itself is weaker. A newly formed black hole and its accretion flow may release less energy into a relativistic jet. A rapidly rotating magnetized neutron star may have different rotational energy or magnetic field conditions. The engine may also remain active for less time. If less energy is available to accelerate the outflow, the resulting jet can carry less relativistic energy and produce a softer, fainter burst. Another possibility is that the engine has plenty of energy, but the jet has trouble using it efficiently. The outflow may contain too much ordinary matter. Accelerating a small amount of material to an enormous Lorentz factor is easier than accelerating a much larger mass to the same speed. Add enough baryonic material to the jet, and the available energy has to be shared among more particles. The jet may remain relativistic without reaching the extreme Lorentz factors associated with the hardest classical GRBs. That reduces the Doppler boosting. The observed photon energies can shift downward. A gamma-ray roar can become an X-ray whisper. The star itself can also interfere. the engine begins launching a jet from deep inside the collapsing progenitor. That jet must cross stellar material before escaping. A compact stripped star offers one kind of route. A denser or more extended structure offers another. If the jet spends more energy clearing a channel through the star, less may remain in the fastest material afterward. If the engine shuts down before breakout, the jet can become choked. It never develops into the classical GRB jet we would detect from far away. But the energy deposited inside the star does not disappear. It can inflate the cocoon surrounding the jet. It can strengthen shocks. It can contribute to the supernova. Some high-energy radiation may still escape from wider, slower material. Such an event could appear much softer than a successful classical GRB. Then there is shock breakout. A supernova shock moving through the star can eventually reach material thin enough for radiation trapped behind the shock to escape. If the star is surrounded by dense stellar wind, the effective breakout may occur in that wind rather than exactly at the stellar surface. The resulting emission can be strong in X-rays. This offers a different route to a soft transient. Instead of seeing mainly radiation from an ultra-relativistic jet, we may be seeing significant radiation associated with the supernova shock itself. For XRF 060218, a thermal X-ray component was interpreted in early work as possible evidence of shock breakout associated with SN2006AJ. The precise decomposition of the event remains a subject of detailed modelling, but the important lesson is straightforward. An X-ray flash can contain more than one physical component. The central engine may contribute, the jet may contribute, the cocoon may contribute, the supernova shock may contribute, and the balance between them can be very different from the balance in a classical GRB. Viewing angle adds another layer. Even a powerful structured jet may contain a very energetic central core surrounded by slower, less energetic material. An observer looking near the core sees a hard gamma ray burst. Another observer farther from the axis may see radiation mainly from the weaker outer regions. The same explosion can therefore look very different from different directions. As the jet slows, the afterglow may eventually reveal the energetic core. That is why weighting matters. The prompt flash can mislead. The afterglow has fewer places to hide. Not every clue arrives in the same wavelength. X-rays are useful early because high-energy electrons in the external shock can produce detectable X-ray synchrotron emission soon after the burst. Optical observations can identify the host galaxy, and sometimes measure a redshift. Radio observations probe slower and later evolution. A supernova can emerge after the bright early afterglow fades. The entire event gradually separates into parts that were originally piled on top of one another. There is a practical example in the optical light curve. Immediately after a burst, the fading afterglow may dominate. Its brightness drops. Several days later, instead of continuing along the same smooth decline, extra light begins appearing. That additional light can be the associated supernova becoming visible. At first, it was hidden beneath the brighter afterglow. Now the afterglow has weakened enough for the stellar explosion underneath to show itself. Spectroscopy can confirm the connection. Broad features in the spectrum reveal rapidly expanding supernova ejecta. The absence of strong hydrogen features and the properties of the spectrum can identify a Type 1c explosion. Now astronomers are no longer inferring that a massive star probably died. They are watching the supernova created by that death. For XRF 060218, the association with SN2006AJ helped extend the GRB supernova connection into softer and weaker high-energy events. That was important because the GRB supernova relationship had previously been demonstrated most dramatically using unusually energetic Type 1c supernovae. SN2006AJ showed that an X-ray flash could accompany a less extreme stellar explosion. It suggested that the boundary between ordinary core collapse supernovae and the spectacular GRB supernovae might contain intermediate cases. Instead of two boxes, there may be a range. Ordinary supernova, engine-driven supernova with modest relativistic ejector, X-ray flash, low luminosity gamma-ray burst, powerful classical GRB. Those labels are useful, but the underlying physics may change gradually across parts of that sequence. That would also explain why weak events can be difficult to understand from observed numbers alone. A classical GRB is so luminous that detectors can see it from an enormous distance. A low luminosity XRF cannot be detected across the same volume. Even if weaker events happen far more frequently, most occur too far away to trigger our instruments. The ones we discover tend to be nearby. That creates a selection effect. Suppose one type of explosion is visible across a region of space containing millions of galaxies. Another can only be detected across a region containing a few thousand. You may detect more of the first type, even if the second type happens much more frequently per galaxy. The bright events advertise themselves across the observable universe. The weak ones have to occur close enough for us to notice. This is one reason low luminosity GRBs and XRFs are interesting for understanding how often massive stars launch relativistic or mildly relativistic outflows. The classical GRBs may represent the obvious successes. There could be a much larger population of weaker engines, partially successful jets, choked jets, and softer explosions that current instruments detect only when they happen comparatively nearby. In that sense, the whisper may be common. We simply cannot hear it from as far away. There is another clue hidden in afterglows that became especially apparent after Swift began observing bursts rapidly. The X-ray brightness does not always decline in a simple way. Some bursts fade very steeply just after the prompt emission. Then the decline becomes much flatter. Astronomers call this flatter period a plateau. Later, the source resumes a steeper decline. Other bursts show sudden X-ray flares long after the main gamma-ray emission has ended. These features are difficult to explain using only a single blast wave that received all its energy at the beginning and then coasted outward. They suggest that the engine or ejector can remain complicated after the prompt phase. Perhaps the central engine continues supplying energy. Perhaps slower shells launched earlier catch up after the front of the blast wave begins decelerating. Perhaps magnetic activity near the compact remnant produces late episodes of energy release. The details differ between models, but the broad lesson is clear. The engine may not switch off neatly when the prompt burst ends. That matters when considering XRFs. A weak prompt flash does not automatically mean the central object itself was weak in every sense. Energy can appear later. It can be placed into slower ejector instead of the ultra-relativistic material that makes bright gamma rays. It can be released over a longer period. Two stellar explosions with similar overall energy could divide that energy very differently. One might place a large fraction into a narrow ultra-relativistic jet and produce a bright GRB. Another might place more into slower supernova ejector and only a small fraction into mildly relativistic material. To a gamma-ray detector, those events look radically different. To the star's total energy budget, the difference can be less dramatic. That is why astronomers try to measure the entire explosion rather than only the first flash. The prompt X-rays tell one part of the story, the radio tells another. The supernova carries most of its kinetic energy in much slower material. The compact remnant may continue adding energy. Only after combining these components can researchers ask how powerful the death really was. Environment matters as well. A massive star can spend its final life losing gas into the space around it. A strong stellar wind can produce a density that decreases outward. Binary interaction can alter the surroundings. Earlier episodes of mass loss may create shells of material. When the blast wave encounters these structures, the afterglow can respond. A denser region may increase emission. A sudden change in density can modify the light curve. Absorption in surrounding material can affect X-rays. Dust can weaken optical light. So a faint optical afterglow does not automatically indicate a weak explosion. It may simply be hidden by dust. A faint X-ray signal has its own ambiguities. Again, every wavelength acts as a check on the others. Astronomers are trying to separate what belongs to the explosion from what belongs to the environment and what belongs to our viewing position. It is a difficult reconstruction, but the fading itself helps. As one component weakens, another becomes easier to see. The prompt burst disappears and exposes the early afterglow. The early afterglow fades and exposes the supernova. The relativistic ejecta slow and reveal their total energy through radio emission. Weeks and months pass, and the environment becomes part of the measurement. The explosion becomes dimmer while our understanding of it improves. That is a slightly unusual feature of transient astronomy. The brightest moment is often not the most informative one. During the flash, the detector is overwhelmed with activity from a source that has just appeared without warning. Later, when the excitement is quieter, astronomers can begin separating the parts. How fast is the X-ray flux declining? Does the spectrum soften? Is there a jet break? Does the optical light follow the same trend? Is the radio source brighter than expected? Does an off-axis jet emerge? Is there a supernova underneath? How energetic are its ejecta? How far away is the host galaxy? Each question places another limit on what could have happened inside the star, and sometimes the answer is that the star did not fail to produce a gamma-ray burst in one simple way. There may never have been a powerful classical jet. There may have been one that stalled. The outflow may have been slower. The observer may have been off-axis. The radiation may have included shock breakout. The central engine may have divided its energy differently. Several of those conditions may occur together. This is why the word whisper should not be mistaken for weakness in every part of the explosion. A star can eject several solar masses of material at thousands or tens of thousands of kilometers per second and still produce a weak high-energy transient. The supernova can be enormously energetic by ordinary standards, while its relativistic component remains modest. What makes a classical GRB exceptional is not only that a massive star exploded, it is that a significant amount of energy became organized into an ultra-relativistic outflow capable of producing brilliant gamma radiation in our direction. Change that one part of the energy distribution, and the same general kind of stellar death can look much quieter to a satellite. The afterglow tells us how much of that fast outflow survived. The supernova tells us what happened to the rest of the star. By the time astronomers have followed the fading X-rays, watched the radio source expand, measured the supernova, and estimated how much energy went into fast-moving material, they can begin asking a much harder question. What was sitting at the center of the explosion? The difficulty is that this is the one object we cannot simply photograph. The star has collapsed around it. The surrounding region is filled with hot plasma, expanding ejecta, shocks, magnetic fields, and radiation. If a black hole is formed, it emits no light from inside its event horizon. If a neutron star survives, it may be only a few tens of kilometers across and located in a galaxy millions or billions of light years away. So astronomers do not see the central engine directly. They see what it does. They measure how long energy continues to emerge. They estimate how much material becomes relativistic. They examine whether the X-rays shut off rapidly or continue for hours, days, or weeks. They look for patterns suggesting a rotating object losing energy. They compare the supernova with the high-energy flash. Then they try to determine what kind of compact object could have powered everything. For long gamma-ray bursts, one of the oldest and most influential possibilities is a newly formed black hole surrounded by rapidly accreting material. The basic situation begins during core collapse. The center of the massive star falls inward. A black hole forms. But because the star was rotating, some of the surrounding matter has too much angular momentum to fall directly into the black hole. Instead, it forms an accretion disk. The word disk sounds calm. A compact disk around a newborn stellar mass black hole is not calm. Matter is moving at a substantial fraction of the speed of light. Temperatures can become extreme. Magnetic fields become amplified. Material spirals inward and releases enormous amounts of gravitational energy. Part of that energy disappears into the black hole with the accreting matter. Part can escape. Under suitable conditions, magnetic fields and the rotation of the system can help launch relativistic jets along the rotational axis. This is the basic collapsor engine associated with many models of long gamma-ray bursts. The fuel supply comes from the star itself. Material falls toward the newly formed black hole. The disk processes that material. The engine remains active while enough matter continues feeding it. If that accretion rate is high and the jet is powerful, the result may be a classical long gamma-ray burst. If the system produces less power, operates differently, or places less energy into ultra-relativistic material, the observed event could be much softer. That makes a black hole engine entirely capable of producing something in X-ray flash territory. A black hole does not automatically guarantee a brilliant GRB. The outcome depends on the disk, magnetic field, rotation, fuel supply, jet formation, and the star surrounding the engine. One black hole can be fed efficiently for a useful period. Another may receive material in a less favourable configuration. One jet escapes. Another struggles. The central object can be similar while the final observable event is very different. There's also something called fallback. Not all material thrown outward during the initial explosion necessarily escapes the star forever. Some ejector may move too slowly to overcome gravity. It travels outward for a while, slows, and eventually falls back toward the compact remnant. If the remnant is a black hole, that returning material can provide additional fuel. Accretion can therefore continue or restart after the earliest phase of the explosion. This offers one possible way to produce prolonged central engine activity. A burst may have finished its brightest prompt emission, yet X-rays continue appearing later because the central region is still receiving matter. Flares can occur, additional energy can be injected into the outflow. The engine may decline gradually rather than switching off at one exact moment. That becomes interesting when the X-ray light curve refuses to behave like a simple blast wave. If the external shock alone cannot explain the continuing emission, astronomers begin wondering whether the central engine is still operating. A black hole fed by fallback is one option. But there is another compact object capable of storing an astonishing amount of energy, a newborn neutron star. More specifically, a very rapidly rotating, highly magnetized neutron star, a magnetar. Ordinary neutron stars are already extreme objects. Take something with a mass comparable to the Sun and compress it into a sphere roughly the size of a city. The surface gravity becomes enormous. The density becomes enormous. Rotation can be extremely rapid. Magnetic fields can be vastly stronger than anything produced routinely on Earth. A magnetar pushes the magnetic part even farther. Known magnetars possess exceptionally strong magnetic fields, and newborn magnetars proposed as GRB engines could begin life spinning extraordinarily quickly, perhaps completing a rotation in only a few milliseconds. That gives the object a huge reservoir of rotational energy. A rapidly spinning neutron star does not have to keep that energy. Its magnetic field can act as a mechanism for extracting rotational energy and transferring it into the surrounding environment. As the magnetar spins down, it can power an outflow. If the conditions are right, that outflow can become relativistic. Now we have a second possible central engine. Instead of matter falling through a disk into a black hole providing most of the available power, the explosion can draw heavily on the rotational energy of a neutron star. Both systems can potentially launch jets. Both can create long-duration high-energy transients. Both can continue influencing the explosion after the initial core collapse. And from billions of light-years away, distinguishing between them is not easy. One possible clue is the total energy. A magnetar has a large but finite rotational energy reservoir. For a neutron star rotating near the fastest physically allowed rates, the available rotational energy can reach roughly a few times 10 to the 52 ergs, depending on the mass, radius, and rotation. That is enormous. But it creates a useful upper scale. If an explosion appears to require much more energy, than a plausible neutron star can provide, a black hole accretion engine becomes more attractive. A black hole does not have the same simple, rotational energy ceiling, because energy can continue being supplied by accreting matter, and a rotating black hole itself can also contribute energy through magnetic processes. The problem is that estimating the true energy of a GRB is difficult. Remember the jet. If the radiation is strongly beamed, the isotropic equivalent energy can greatly exceed the actual energy released. So before using energy to choose between a black hole and magnetar, astronomers need to understand the geometry. That is one reason afterglow measurements matter so much. Another possible clue comes from how the X-ray light changes with time. Some GRB afterglows show long plateau phases. Instead of simply declining at the expected rate, the X-ray brightness remains relatively flat for hundreds or thousands of seconds before falling more steeply. One explanation is continued energy injection from a spinning magnetar. A rapidly rotating magnetized neutron star naturally loses rotational energy over time. Under some conditions, the resulting spin-down power can remain fairly steady at first and then decline. That can produce an X-ray light curve resembling a plateau followed by a steeper decay. This does not prove a magnetar is present. Other mechanisms can create plateaus. Slower ejector can catch the blast wave and inject energy. Black hole accretion can continue. The radiation efficiency can evolve. But a plateau provides one of several clues researchers use when testing magnetar models. Sometimes the decline after a plateau becomes extremely steep. That creates an especially interesting possibility. Imagine a rapidly rotating neutron star formed immediately after collapse. Its rotation temporarily helps support it against gravity. The star powers an outflow. We see extended X-ray emission. Then the neutron star loses enough rotational energy that it can no longer support its own mass. It collapses into a black hole. The central power source changes abruptly. In some models, that could produce a sharp drop in the X-ray light curve. The engine was first a neutron star, then it became a black hole. So asking whether the central object is a black hole or magnetar may occasionally be the wrong question. It might be both, one after the other. This possibility is especially relevant in other types of gamma-ray bursts, including some events associated with compact object mergers, but the broader lesson applies here. Compact remnants can evolve. The object present 1 second after collapse may not be the object present an hour later. For X-ray flashes connected with massive star deaths, that gives astronomers another set of possible histories to test. XRF 060218 has played an important role in these discussions because it was unusually nearby, unusually soft, unusually long, and connected with the Type 1c supernova SN2006AJ. Early modelling of the supernova suggested that its progenitor may have been less massive than the progenitors of some famous GRB-associated supernovae. Some researchers argued that the explosion may therefore have left behind a neutron star rather than forming a black hole immediately. That made a magnetar-like engine particularly attractive. At the same time, radio and X-ray observations showed that the event had a genuine central engine and mildly relativistic ejector, setting it apart from ordinary Type 1bc supernovae. The exact engine has never been photographed, and different models continue to interpret parts of the event differently. That uncertainty is useful to remember. Astronomers can say that a central engine was involved with much more confidence than they can say exactly what the engine was. This is common in astrophysics. Evidence can narrow a problem dramatically without reducing it to one answer. XRF 060218 was not simply an ordinary spherical supernova. It produced fast ejector. It produced long-lived X-rays. It had a soft high-energy transient. Something near the centre remained dynamically important. Whether the final compact remnant was a neutron star, a magnetar, or a black hole depends on details that the observations constrain but do not uniquely settle. Then there are possibilities that do not fit neatly into either basic picture. Consider a choked jet again. A central engine may successfully launch a relativistic outflow, but fail to send it all the way through the star. The jet deposits energy into the stellar interior. A cocoon forms. Shock waves move outward. The engine can therefore be very real, even if no classical gamma-ray jet escapes. What reaches Earth may be dominated by softer X-rays from shocks, breakout, or slower material rather than by the narrow ultra-relativistic core we associate with classical GRBs. In that case, the central object might be capable of producing a powerful jet, while the surrounding star prevents us from seeing it in the usual form. Recent modelling of low luminosity GRBs, including GRB 060218, continues to examine versions of this idea. In some models, a jet deposits a large amount of energy into an extended low-mass envelope surrounding the progenitor, and the resulting shock breakout can reproduce important features of the long, soft X-ray signal. That is a reminder that the central engine is not the only thing determining what we observe. The engine produces energy, the star processes it, the surrounding material processes it again. Relativity changes what reaches different viewing angles. Cosmic expansion shifts the photon energies before they reach Earth. Then the detector samples only part of the spectrum. By the time we call something an X-ray flash, many physical filters have already acted on the original event. This is why XRFs can tell us more than simply how massive stars die. They help researchers study how relativistic explosions work as a population. At one end are the bright classical GRBs detected across enormous distances. Their jets are successful. Their relativistic components are powerful. Their radiation can be strongly beamed. At another end are ordinary core collapse supernovae with no evidence for substantial relativistic ejecta. Between them are objects such as low luminosity GRBs and XRFs. These intermediate events may tell us how often massive star collapse produces an engine, even when the engine fails to create a classical GRB. That is a major question. Perhaps only a tiny fraction of massive stars create central engines capable of launching relativistic jets. Or perhaps engines are more common, while successful, highly relativistic jets are rare. Those two universes would look similar if we counted only the brightest GRBs. XRFs give us access to less obvious outcomes. Suppose many collapsing stars attempt to launch jets. Some succeed spectacularly. Some escape weakly, some are choked, some produce mostly mildly relativistic ejecta. Some are directed away from Earth. The bright gamma-ray population would then represent only the visible tip of a much larger collection of engine-driven stellar deaths. This has consequences for estimating how often black holes and magnetars are born in particular ways. It affects our understanding of how massive stars rotate before collapse. It constrains how efficiently jets can penetrate stellar envelopes. It can tell us about mass loss from stars before they explode. And it helps connect ordinary supernova physics with the relativistic universe. There is also a chemical connection. Massive star explosions distribute newly created elements into surrounding space. The details of the explosion determine which layers escape, how quickly they move, and how radioactive material is mixed through the ejecta. GRB-associated Type EC supernovae often show broad spectral features indicating very high velocities. XRF-associated supernovae can provide intermediate cases. By comparing them, astronomers can test whether stronger central engines systematically produce different supernova properties. The relationship is not perfectly simple. A jet may contain only a small fraction of the total explosion energy, while still dominating what a gamma-ray telescope sees. The bulk of the star can carry vastly more mass at much lower speeds. So two supernovae with similar total kinetic energies might produce very different high-energy signals if one places more energy into a tiny amount of ultrafast material. That tiny relativistic fraction matters enormously. A normal supernova can eject several solar masses and still remain nearly invisible to a gamma-ray burst detector. Another explosion can direct a much smaller amount of matter into a relativistic jet and suddenly become visible across a large fraction of the observable universe. XRFs occupy the useful region where that relativistic component exists but may be weaker. They help researchers measure how the energy distribution changes between slow supernova ejecta and the fastest jet material. The same events can also teach us about star-forming environments. Long GRBs and XRFs associated with massive star collapse occur in galaxies where young massive stars can exist. By studying their host galaxies, astronomers can examine metallicity, star formation rate, stellar population, and other properties that may influence whether a dying star retains enough rotation to produce an engine-driven explosion. Metallicity is especially interesting. Astronomers use that term to describe the abundance of elements heavier than helium. Massive stars with different metallicities can lose mass at different rates through stellar winds. Mass loss also removes angular momentum. Since rotation is important for producing a disk or rapidly spinning compact remnant, the star's chemical environment can influence whether it reaches collapse with enough angular momentum to power a relativistic outflow. Binary companions complicate things further. A star can lose its hydrogen envelope through interaction with a companion rather than through wind alone. Mass can transfer between the stars, the orbit can alter rotation, the stars can even merge. So when astronomers find an XRF in a particular type of host environment, they are collecting information about the entire life of the progenitor, not just its final seconds. There is another reason low luminosity events matter. They may be far more common than they look. A classical GRB can be detected from billions of light years away. A weak XRF may need to occur relatively nearby before our instruments can identify it. The volume of space available for detecting the bright event is therefore much larger. Even a common weak population can produce fewer detections than a rarer luminous population. XRF 060218 helped draw attention to this possibility. Radio and X-ray studies estimated that events resembling it could occur substantially more often than cosmological GRBs, while carrying far less energy in relativistic ejecta. If that is broadly true, the spectacular GRB is not the standard result of engine-driven collapse. It is the extreme result. The quieter events may be telling us what usually happens when the engine is less successful. That changes how we think about black hole and neutron star formation. Instead of asking only what produces the brightest bursts, researchers can ask how the engine behaves across an entire distribution of outcomes. Does a black hole tend to produce the hardest jets? Can a magnetar naturally produce more of the weaker, softer events? Do choked jets occur much more often than successful ones? Can the same kind of engine produce both outcomes depending on the progenitor structure? Is shock breakout sometimes responsible for the observed X-rays even when a jet exists underneath? Those questions remain active because the evidence does not support one simple rule. Both black hole and magnetar engines remain viable in models of long GRBs. Low luminosity bursts and XRFs add important constraints, but they do not provide a universal engine label. That is not a failure. It means these events are giving us enough information to distinguish multiple physical routes through stellar collapse. And there may be stranger routes still. A rapidly spinning neutron star might power the explosion for a while, and later become a black hole. A black hole may form through fallback rather than immediately at core collapse. A jet may start narrow and become heavily disturbed inside the star. Binary evolution may create progenitors unlike the isolated massive stars used in simpler models. An extended envelope may transform jet energy into a long soft breakout signal. In February 2026, astronomers were even discussing the nearly 7-hour GRB 250702b in terms of an unusual possible black hole helium star merger, because its duration and energetics appeared difficult to fit into several conventional engine models. That event is not an XRF, and does not rewrite the interpretation of XRFs. It simply demonstrates that the broader high-energy transient sky continues producing stellar explosions that test the categories we build. That is useful context. When an X-ray flash arrives, astronomers do not begin with the assumption that every soft event must fit one established diagram. They compare it with what is already known. They ask whether there is a supernova. They measure the host. They study the spectrum. They watch the afterglow. They search for late engine activity. They estimate the relativistic energy. They test viewing angle models. Then they ask what kind of compact object and stellar environment could reproduce all of those observations at once. Sometimes a black hole is the strongest explanation. Sometimes a magnetaire is attractive. Sometimes the data are not sufficient to choose. And sometimes the most interesting answer is that the classification itself may be hiding several different physical mechanisms. What X-ray flashes give us is not a direct view of the remnant. They give us a controlled way to test what remnants can do. A black hole can accrete, a magnetar can spin down, a jet can fail, a shock can break out, fallback can restart activity. A structured outflow can look completely different from another angle. The observed flash is the consequence of all those processes competing during the same stellar death. That is why a soft signal can carry so much information. It sits between the ordinary supernova and the classical gamma-ray burst, forcing astronomers to explain not only why some stars produce spectacular relativistic jets, but why other stars almost do. By understanding those near misses and intermediate explosions, we learn which ingredients are essential: rapid rotation, compact object formation, magnetic fields, accretion, envelope structure, mass loss, viewing geometry, and the ability of a relativistic outflow to survive the trip from the centre of a star into open space. The first X-ray flash detected by a satellite may appear to be a brief pulse on a screen. After enough follow-up, it becomes something much larger, a measurement of how a massive star collapsed, a test of how black holes and neutron stars are born, a probe of relativistic jets, a record of the material surrounding the progenitor, a way to count explosions too weak to be seen across most of the universe. But the flash did not reach us when the star died. What finally reaches Earth is not the star. It is not the black hole, the neutron star, the jet, the shock wave, or the supernova ejector. It is information. A small number of photons arrive at a detector after travelling through space for millions or billions of years, and from those photons astronomers try to reconstruct an event that may have lasted only a few minutes. That is the strange advantage astronomy has over almost every other science. We cannot place a massive star in a laboratory and ask it to collapse again while we adjust the instruments. We cannot move Earth a few degrees to the side and watch the same jet from another angle. We cannot restart a black hole engine with different magnetic fields and compare the result. The event happens once, the light leaves, and whatever information is encoded in that light is what we get. An X-ray flash is one of those messages. At first, it may look surprisingly modest. A satellite notices a temporary increase in X-rays. The source appears where there was no known bright X-ray object a moment earlier. The signal rises, changes and fades. Perhaps the gamma-ray detector sees very little. Perhaps the spectral peak sits at only a few kilo-electron volts. Perhaps the entire event lasts several minutes. Then the brightest part is over. Nothing about that description immediately tells you that a massive star may have collapsed, a compact object may have formed, a relativistic outflow may have fought its way through stellar material, and a supernova may now be expanding into the surrounding galaxy. Those conclusions have to be extracted from the details. The energy distribution of the photons is one clue, the duration is another. The shape of the light curve tells astronomers whether the source released its energy smoothly or in several episodes. A changing spectrum can reveal how the emitting material evolved. A thermal component can suggest hot matter with a characteristic temperature. A broad non-thermal spectrum points toward energetic particles and relativistic radiation processes. The X-ray afterglow tells us what happened after the initial flash. The optical counterpart can identify the host galaxy. A redshift gives the distance scale. Radio observations estimate how much energy went into fast ejector. Then, if the event is close enough, the light from a supernova begins to emerge. None of those measurements alone provides the entire story. Together, they can turn an unexplained flash into a physical history of a dying star. This is what happened with XRF 060218. Swift detected the event on February 18, 2006. It was unusual immediately. The high-energy emission lasted roughly 2,100 seconds, about 35 minutes, far longer than many ordinary gamma-ray bursts. It was also unusually soft. Its spectral peak sat around only a few kilo-electron volts, placing it firmly in the X-ray flash part of the broader GRB population. Swift automatically turned toward the source and began observing it with its X-ray and ultraviolet instruments while the event was still developing. That rapid response allowed astronomers to follow the explosion through phases that would once have been missed entirely. A few days later, the source was associated with SN2-006AJ. Now the soft burst had a supernova attached to it. The star had not simply produced an unexplained X-ray transient, it had died. And because this particular event occurred relatively nearby by GRB standards, astronomers could study the connection in unusual detail. That is one reason XRF 060218 has appeared so often in our discussion. It is not the only X-ray flash. It is simply one of the clearest demonstrations of why these events matter. Before cases like this, an XRF could be treated mainly as a strange member of the high-energy transient population. Afterward, it became much harder to avoid the stellar collapse connection. At least some XRFs are telling us about the deaths of massive stars. The remaining problem is understanding why the message arrives in X-rays rather than as a bright classical gamma-ray burst. Earlier observations with Beppe-Sachs had already revealed that some transient sources appeared strongly in X-rays, while producing little or no triggering signal in the satellite's higher energy gamma-ray monitor. HETE2 then showed that X-ray flashes, X-ray-rich gamma-ray bursts, and classical gamma-ray bursts did not form three perfectly isolated groups. Their properties blended into one another. The spectral peak moved. The energy fluence changed. The relative amount of X-ray and gamma-ray emission shifted. But the overall population looked continuous. That changed the question. Instead of asking whether XRFs were completely unrelated objects, astronomers began asking what physical parameter could move an explosion from one end of that continuum to the other. There are still several possible answers. The jet may be less energetic. Its Lorentz factor may be lower. It may contain more ordinary matter and therefore accelerate less efficiently. The central engine may operate for a different length of time. The jet may struggle to cross the star. A cocoon may contribute more strongly to what we see. Shock breakout may add soft X-ray emission. The observer may sit outside the brightest central region of a structured relativistic outflow. Distance can shift the spectrum as the universe expands, and different events may combine those effects in different proportions. That uncertainty is not a reason to regard XRFs as poorly understood leftovers. It is exactly why they are useful. A classical gamma-ray burst shows us what happens when a relativistic stellar explosion produces a very successful high-energy signal. An X-ray flash asks what happens when some part of that process changes. Think about everything that has to work for a bright long GRB to appear. The progenitor must reach collapse in an unusual condition. The core must retain enough angular momentum. A compact central engine has to form. Energy has to be supplied rapidly. A relativistic outflow has to develop. That outflow has to avoid becoming too heavily loaded with ordinary stellar matter. It has to survive the trip through the star. It has to emerge. It has to accelerate. It has to dissipate energy into radiation. And for the brightest observed gamma-ray signal, the geometry has to place us in a favourable direction. Change any one of those conditions and the result may look different. Change several, and the difference can become dramatic. So perhaps the surprising thing is not that X-ray flashes exist. Perhaps it would be more surprising if every engine-driven stellar death looked exactly the same. Massive stars do not arrive at collapse with identical masses. They rotate differently. Some have companions. Some have lost more of their outer layers. Some live in environments with different chemical abundances. Their internal magnetic fields differ. Their cores differ. Their surrounding winds differ. Their central remnants may differ. Expecting one universal explosion would be asking a great deal from nature. X-ray flashes give us access to some of that variation. They may show us weaker engines. They may reveal unsuccessful or partially successful jets. They may expose radiation components hidden beneath the brighter emission of classical GRBs. They may help us estimate how many massive stars attempt to produce relativistic outflows, even when those attempts do not end with a spectacular gamma-ray burst. That last point could be especially important. The events we detect most easily are not necessarily the events that happen most often. A bright classical GRB can be seen across an enormous volume of the universe. A weak XRF cannot. But the same low luminosity XRF at a sufficiently large distance, and it may never trigger our detector. The explosion still happens, the photons still leave, they simply become too faint for the instrument to recognize. So the catalogue of detected bursts is not a straightforward census of how stars die. It is filtered by sensitivity. Bright events can advertise themselves from very far away. Quiet events need to happen much closer. This means there may be many more soft or weak engine-driven explosions occurring throughout the universe than the number we observe suggests. Some may never produce a detectable high-energy burst at all. A jet could form and die inside the star. A cocoon could carry energy outward without producing a classical GRB. A weak relativistic component could disappear below our detection threshold. From Earth, we would classify the event as an ordinary supernova unless some other observation revealed the hidden engine. The difference between a normal stellar explosion and a gamma-ray burst may therefore not always be a clean boundary. There could be a population between them. XRFs may occupy part of that population. That makes them useful for answering a broader question about massive stars. How often does core collapse produce a central engine? There is a difference between forming a black hole or neutron star and forming an engine capable of launching a relativistic jet. There is another difference between launching a jet and having that jet successfully escape. And there is another difference between an escaping jet and one whose brightest radiation points toward Earth. A gamma-ray detector sees only the final result of all those selections. X-ray flashes help recover some of the cases that would otherwise be missed. They also help astronomers study the compact object created during collapse. A powerful classical GRB can be explained by a black hole accreting rapidly from a disk. Some softer events may also use a black hole engine, but produce a different outflow. Other observations have encouraged models involving a rapidly rotating magnetar. A newborn magnetar can contain an enormous amount of rotational energy. Its magnetic field can extract that energy as the object spins down. That energy can continue being supplied after the initial collapse. Long-lasting X-ray emission or plateau-like behavior can therefore become a clue. But again, it is not a label. A plateau does not arrive with the word magnetar written underneath it. Black hole accretion can continue. Fallback material can return. Slower ejector can inject energy into the external shock. Several mechanisms can produce prolonged activity. Astronomers have to compare all the evidence. The central engine remains hidden. Its effects do not. That is an important distinction. We may never see the event horizon of the newborn black hole in one of these distant explosions. We may never resolve the surface of the neutron star, but if the compact object continues supplying energy for thousands of seconds, the light curve can record that activity. If the engine shuts down abruptly, that can leave a different signature. If a relativistic jet carries unusually little energy, radio observations can reveal it. The hidden object leaves fingerprints on material thousands, millions, and eventually billions of kilometers away from it. Those fingerprints become the message. Even the supernova adds information about the engine. A broad-lined Type 1c spectrum tells researchers that ejecta reached high velocities. The brightness of the supernova helps constrain the radioactive material produced. The expansion speed tells us about kinetic energy. Comparing an XRF-associated supernova with a classical GRB supernova and an ordinary Type 1c supernova shows where the event sits within a larger range of stellar explosions. That comparison can be more useful than the original label. A star does not know whether its explosion will be filed under XRF, GRB, low luminosity GRB, or engine-driven supernova. Those are human categories created after the photons arrive. The physical event contains continuous variables: energy, mass, velocity, rotation, magnetic field strength, opening angle, viewing angle, density, duration. Those quantities can vary gradually even when our labels do not. One reason high-energy astronomy becomes confusing is that we often have to turn continuous nature into discrete names. At some point, a burst is soft enough that we call it an X-ray flash, but there is no physical wall in space where gamma rays stop and X-rays begin. There is no universal switch inside the star labelled GRB on one side and XRF on the other. The categories help us organise observations. The continuum reminds us not to mistake the filing cabinet for the universe, and this is perhaps the most useful lesson of X-ray flashes. They appeared interesting because they did not fit the expected category. A gamma-ray burst-like event arrived with too much of its energy in X-rays. Instead of ignoring that difference, astronomers followed it. They built instruments sensitive to softer radiation. They compared spectra. They measured afterglows. They localized host galaxies. They found associated supernovae. They tested viewing angle models. They searched for hidden energetic jets. They compared black hole and magnetar engines. The strange signal became useful precisely because it did not behave like the obvious example. Science often moves forward in that direction. A theory explains the normal case. Then something appears that almost fits. The temptation is to treat the unusual object as an annoying exception. But exceptions can reveal which parts of the theory actually matter. If an XRF resembles a GRB in duration, afterglow and supernova association, but differs strongly in spectral peak energy, then whatever controls that spectral energy becomes especially interesting. If a weak XRF still contains relativistic ejecta, then the production of relativistic material does not require the energy scale of the brightest GRBs. If no hidden powerful jet appears later, then viewing angle cannot explain that event by itself. Each quiet burst removes another easy answer. It forces the model to become more realistic. There is also something practical about these observations that is easy to forget once we start discussing black holes and relativistic jets. Most of the work begins with numbers in a computer. A detector count rises. Software compares it with the background. An alert is created. Coordinates are calculated. A satellite turns. Another telescope starts taking exposures. Astronomers receive messages containing times, positions, count rates, and preliminary spectra. At that stage, nobody has a picture of a star exploding. They have measurements. The physical story comes later. That is why catching the first photons matters. The earliest emission contains information that disappears quickly. How did the spectrum begin? Was there a thermal component? How quickly did the source brighten? Did the peak energy change? How long did the central activity continue? By the time an optical supernova becomes obvious, some of those questions can no longer be answered unless a high-energy satellite was already watching. A transient event is information with an expiration date. The universe does not replay it. This makes instruments such as BepISAX, HETI-2, SWIFT, Fermi, and other high-energy observatories part of the story in a very direct way. Without broad sky monitoring, most bursts would happen unnoticed. Without rapid localization, follow-up telescopes would not know where to look. Without X-ray sensitivity, soft events could be undercounted. Without optical spectra, host galaxies and supernovae would remain uncertain. Without radio observations, hidden relativistic energy would be much harder to test. Understanding one flash requires many different machines looking at different parts of the same event, and even then the answer can remain incomplete. That is not unusual. The most interesting scientific results often end with fewer possibilities rather than one perfectly certain explanation. An XRF may tell us that a massive star collapsed. It may tell us that a relativistic outflow existed. It may tell us that the event was intrinsically weak. It may rule out a simple off-axis classical GRB. It may show evidence for a supernova. It may suggest shock breakout. It may favour a neutron star engine over some black hole models. But there can still be details we do not know. The exact magnetic field configuration near the engine, the precise composition of the jet, the mechanism that produced each part of the prompt spectrum, the exact viewing angle, the final fate of the compact remnant. Those gaps are not signs that the observation failed. Look at what was reconstructed from the original signal. A detector received a temporary excess of photons. From that, astronomers can infer a dying massive star in another galaxy. They can estimate the distance. They can measure the energy. They can identify a supernova. They can determine that some ejecta were relativistic. They can test whether a hidden powerful jet existed. They can compare the event with populations of other bursts. They can ask whether the central object became a black hole or neutron star. That is a great deal of information from a flash that might last less time than a quiet evening routine. There is another detail worth remembering. When Swift detected XRF 060218 in 2006, the star had not just exploded in 2006. Its host lies at a redshift of about 0.033, corresponding to a distance of hundreds of millions of light years. The stellar death happened hundreds of millions of years before the photons reached Swift. The signal spent all that time travelling through space. Earth continued orbiting the Sun. Species appeared and disappeared. Continents changed. Humans evolved. Telescopes were invented. X-rays were discovered. Spaceflight became possible. Engineers built a satellite specifically capable of noticing high-energy transients, and eventually photons from that old explosion reached the detector. From the star's point of view, there was no delay. It exploded. The radiation left. From ours, we received the news very late. Astronomy works this way constantly. Looking farther away means looking further into the past. An XRF from a distant galaxy is therefore both an explosion and a historical record. Its photons preserve information about a star that no longer exists in the form that produced them. Somewhere at that location today, the supernova debris may have expanded far beyond its original size. The compact remnant may have been evolving for hundreds of millions of years. If a black hole formed, it has been there the entire time the burst radiation was crossing intergalactic space. If a neutron star formed, it may have slowed dramatically since its first moments. We do not see any of that when the flash arrives. We see the beginning. That makes an X-ray flash a particularly literal last message from a dying star. Not because the star intentionally sent anything, and not because the signal contains words. The message is simply physics. The photon energies tell us about the radiation process. The timing tells us about the engine. The afterglow tells us about the outflow. The spectrum tells us about temperature, particles, and motion. The supernova tells us what happened to the star. The host galaxy tells us where that star lived. The redshift tells us how long the information travelled. Nothing needs to be added. The event recorded itself in radiation. Our job is to read it. There are still XRFs waiting to be found. Some may occur nearby enough for detailed follow-up. Others will appear at greater distances and provide only a few clues. Future high-energy surveys will likely discover soft transients that do not fit the examples we already know. Some will probably turn out to be members of familiar populations viewed under unusual conditions. Others may force astronomers to change the categories again. That would be perfectly normal. The original X-ray flashes became important because the universe was already doing something our categories had not fully captured. There is no reason to assume it has stopped. So the next time you look at an ordinary night sky, there is no way to tell with your eyes whether somewhere beyond those visible stars a distant massive star has just collapsed. The explosion might be hidden in another galaxy. Its jet might be pointed somewhere else. Its brightest radiation might be in a wavelength your eyes cannot detect. And if it happened far enough away, the light may not reach Earth for millions of years. The sky can look completely unchanged while an X-ray detector in orbit records something extraordinary. That is the world X-ray astronomy gives us, not a different universe. The same universe, viewed with information our eyes happen to miss. An X-ray flash begins as one of the quieter signals in the family of relativistic stellar explosions. It does not always produce the hard gamma-ray spectrum of a classical GRB. It may be weaker. It may be slower. It may be viewed from a different direction. It may contain radiation from shocks or a cocoon that would be less obvious in a brighter event. But the softer signal does not make the underlying event unimportant. Sometimes it makes the event more revealing. A brilliant gamma-ray burst shows us the most successful version of a relativistic stellar explosion. An X-ray flash shows us what happens when the process is different, and those differences are exactly what help us work out how the process works. We began with a brief flash arriving from a dying star. Along the way, that signal led us into the core of a massive star, through nuclear burning and collapse, past neutron stars and black holes, into relativistic jets, shock waves, afterglows, supernovae, and the instruments designed to catch events that disappear almost as soon as they begin. The original question sounded simple. What is an X-ray flash? The observational answer is still simple enough. It is a brief high-energy transient whose prompt radiation is unusually soft and strongly concentrated in X-rays compared with classical gamma-ray bursts. The physical answer is more interesting. It can be evidence of an engine-driven stellar death, in which the jet, engine, geometry, or surrounding material produced a softer version of the larger GRB phenomenon. Exactly which combination produced a particular XRF has to be determined event by event. That is where the mystery remains. And perhaps you are still awake after all of this, which means the central engine of this particular sleep experiment has been remarkably persistent. Wherever you are listening from, the stars above you are carrying information from many different times. Some of that light left its source a few years ago. Some left thousands of years ago. Some began crossing the universe before Earth existed. We receive each signal when it reaches us, not when the event happened. An X-ray flash is simply one of the briefest examples. A star can spend millions of years living, collapse in seconds, produce high-energy emission for minutes, and leave astronomers studying those few minutes for decades. That seems like a fairly good return on a very short signal, and if another soft flash reaches one of our satellites tonight, computers may already be measuring it before anyone knows that a distant star has left one more set of clues behind. For now, though, there is nothing you need to measure. No spectrum to fit. No afterglow to chase. No satellite alert requiring attention. If you found this journey through collapsing stars, X-rays, and relativistic jets interesting, you can leave a like and subscribe to Science for Sleep. It helps these quiet science journeys reach other people who enjoy learning something before the day finally switches off. And wherever you happen to be listening from, whether there are stars outside your window or just a very determined street lamp, you can let the detectors keep watching the high-energy universe for you. They are much better at staying awake.